And once again, here you have it, a freshly formulated, high-quality feed recipe at the lowest possible price. The feed calculator is the perfect solution, not only for Henry, but also for millions of other livestock farmers all over the world. Download the app now from Google Play
Halo.
There will be a presentation. So I would like to invite our director, Dr. D.K. Das, ICAR, to give a lecture on drone application in fisheries management.
All of you. To begin with the session, you could look into the advancement beneath the fisheries. It is not as per the other sectors they are growing in the drone applications. But you could see in the fisheries sector, we are approaching because as you know, it's an underwater system, most of the things. And most of the surface water can be mapped, and this is the technology that are going. But because of turbidity and other factors, there are a lot of maybe noising will come when you go for any type of thing. So you have to balance all these things. As all of you know, the drone technology. Initially, people thought maybe we are hard, maybe 5-6 years back when it is COVID and other things came. So starting with the transportation of the medicine to the difficult places, life-saving medicine, the humble beginning, and with the technology or later on the defense, how it is comes. But in the end, we thought that maybe policy and planning level, just like Dr. Ravi told that Fisheries Institute and Animal Sciences added when this project came. So with that humble beginning as you told, the project launched in September, we have a patent on October. Means that prior to that, we have taken something in the institutionalized with the help of that how to build one, even at that time.
5,800.
म्यूट आप सबको अनम्यूट कर दीजिए ना. So with that humble background, we started initially the drone systems we started, that is means we just that time initially drone was so costly to this. So again we started water sampling, nonsense reversing, because we cannot file a patent on the drone in the as such. What we do to the sensing operation of the water collections, nonsense reversing water, you might have heard the name scientist when you go to the different depth of collect the water, Nansen, the scientist, develop a system how to collect in the different depth of the water, to measuring whether it is a phototropic, apoptotic, or the plankton levels in the different depth. So in that concept, we design a sensor based, because it will open in a particular depth. Again, the sensor through it will see your command system, it will close, collect the water, bring to the thing. So that is the things. Again, all of you know how the Indian fishery sector is growing as an average of 9%, surpassing all sectors in the agriculture. It is a fastest growing sector. Again, all of you know the climate change is a major problem block that is taking a major role. Maybe if you are going a Katla breeding in a system, it is very difficult because Katla is a algae breeder. It's very difficult. Or you have some infrastructure in a lot of inland sector, less infrastructure. Even in marine sector, landing center, when you going trawler for fishing, overfishing takes place, lot of fish cannot be transported. So a lot of systems, again, maybe you have a climate forecasting systems, everything is there. Again, like in all sector, we have a less human resources also. Then system for life is transportations. All these things make a mix. So we have make a development like with other sectors, maybe your transportation systems, that is your life fish carriers, water sampling from the inaccessible areas, life jacket delivery systems, second, and maybe third one is inspections in the different systems, monitoring for any illegal catching or something, then monitoring the underwater nets, then health of the case, even if you now large circular case, marine case, inland case, all these things, then water quality monitoring with using sensors. Then if you look to the back. Then it will go to the health management also. Fish health, mainly solo fish, the health disease were there, maybe shrimp pond, lot of shrimp pond, different, all these things. Then you will see broadcasting, feed inputs, all these things, or like your sprayers. These are the things with the satellite systems that are developing the migration part of the different. you will find harvest, it will be there. And their identifications, there you have the, what is the, maybe in the different, maybe hyperspectral imaging, multispectral imaging, what is the coverage of aquatic weeds. Later on, you will extend to the, maybe your different detection of the chlorophyll and other systems, when they can be used for the productivity estimations, or later we can go for the maybe underwater imaging, all these things, and there we can find the visual, everything that can be. Then third one is your PP, one is your nutrition, therapeutics, and husbandry practices. This is mostly, we are mostly with the, your working with the, maybe with your smartphone, you have done in SIPA, there we are working with the sensor, and here we are mostly the applications, we have given an application in the Moina wetlands, in the large pond systems, the like your spraying of the pesticide for arbutus control and other things, then field demonstrations. Again, we have showed it some of the feed, and I told them you can find out the husbandry of the fish health also, whether fish is behavior, fish is eating or not eating, and then the demand, what is the things when you can dispense the feed, that will be controlled based on the sampling, and that is the drone-based imaging that can be given a command. Again, if you have, like I told, like your must be health means fish disease, you can monitor, behavior you can study, then what is the different identification like machine vision, learning also, that can deep learning. So machine vision learning, all these systems you can adapt, integrate with the drone-based systems, then you can find how best it can be work in the fisheries sector also. Again, if you look into the, I told this is the our drone-based water sampler under the project, and we have filed a patent, I told, and this is the simplest you could see. Again, we have designed, like if any chances there is a problem, it will, with these floaters, it can, the drone can be stay in the water bodies, and it can be. So there are two systems, either you can buy system different way, and here you can add the depth meter also, that can give in what depth you can getting the water also, that will be the best instead of measuring other things. So you can put a depth meter, and here also we're integrating with the temperature, turbidity, other sensors that can be articulate all these systems. And as on the sensor technology, sensors will be available us, we will be integrating with the technology partnerships to how best we can see the water mapping, water bodies can be mapped with the all type of real-time monitorings or any spatio-temporal basis in the drone-based system. Again, back. Again, you will see, it is one of the important aspect, like if you are going for like Alkan in the other places, where you do not find any types of boat and other thing, collect the sample and the steep terrain, and where things are there, you can use this type of things. On difficult terrains where inaccessible areas, there, just like you will see, this flood, you will see there is a dam has eroded in Tista 4, TLD 4 in Sikkim. So all those areas, if you are going for sampling, that is more important, that whether if you are like the government of India is declaring the potable water for drinking, bathing, all these things, this quality of things where you cannot approach also, that is the one aspect. Another is a large ponds, like if we go to now in Bengal, people are have a single pond of 300 bighas, and lot of things, I mean 100 acres most, they are coming like your Andhra Pradesh culture systems with less depth and small fish. Where the Andhra Pradesh, there is a large fish there you are getting, but you have a small fish, 100 grams, 200 grams, maybe other, maybe you have Santangra and other fish. In that systems, it is very easy to apply your drone-based systems and see the different hyperspectral imaging, get the analyze the data and get back what is happening, dynamics, and you can remotely manage also your pond instead of putting these things. Again, these are the things. Again, this is one of the important aspect where you can work. Next is your, I told this is the way we have worked, and these are the some of the systems being operated, and this was I told, no, this was inaugurated by our then Director General, Mahapatra sir, and in presence in the Gandhi Ghat, this activity was demonstrated. Again, if you see, we are doing like your sampling in the East Kolkata wetlands also, drone-based sampling here. And this is here because this is a largest Ramsar site, and we call the kidney of the Kolkata. Because large purification, sediment, metals, then sewage, everything. Here the sensor-based, maybe hyperspectral imaging based will give us a clear-cut picture of these wetlands, and accordingly a contingent planning can be developed. That is the most important, because of this is maybe 20,000 people there on fisheries. Means only total sewage is fed, no feed is given, and that nutrient is this thing. So this is more way of maybe a room can monitor and give you when we are going of this type of system, and directly we give one day immediately the what to be done and what not to be done. Again, I told 20,000 people for fisheries. It will integrate because here horticulture, agriculture, everything. 1,50,000 family have their earnings in this. It's the largest beautiful models if you can have a drone based in all aspect, a holistic aspect of agriculture, fisheries can be implemented, and this is a contaminated things in what is happening. We can get back if we really adopt and utilize the sensor based drone technology here, including the underwater drone and other things that will be give a dynamics of the pond equation or wetland equation, because here 260 wetlands are there. And the area of the farming of fish culture has increased from 4,400 to around 6,000 hectares also. A beautiful model can be operated, and we have tried a Bingling how to go, and we have given all demonstration our 3 of the technology with the community participations and aware the people of the application of this technology. Again, then this model is your fish transportation system. This is a conceptual, but we have, I told, already 3 national demonstration has been done, but only now 20 kg, 30 kg, 40 kgs. But we have to develop a, we are things because 20, 30 kg are all available with the drone-based company in India, or 40 kg. So we are trying that maximum level of 100 kg payload. Still, we do not find. We have got up to 70 kg payload that can be used, but the cost, because we have 85 lakhs rupees our ceiling. Within that 85 lakhs, who can come forward? We have a thing, and accordingly, we should see maybe initially this is a pilot project. A prototype will develop, flying other things. Then we have to all requirements be fulfilled. Then can be extrapolate over the country. And it's a challenging. Within 1 year, we have to develop. This is the techniques, and we request anybody can be a partner to this to develop a sustainable systems, and because this will pick up, because many of the things like a farm to like a urban center, when fish, live fish, quality fish, all these things, maybe fresh fish, fresh frozen fish, all the aspect can be brought. Maybe somewhere trawler is going, maybe it's over loaded of these things, there can become the fish also. Maybe most of the trawler have the, maybe they on the platform, they can, you can lend your drone also, and from there you can fly also. But we have to see the flying time, how much kilometers it can fly, and what is the hour of battery backup. And if we are designing also, these are the things to be seen, and that can be maybe applicable to so many aspects also. Next. Then I told this is a macrophyte coverage area from aerial drone image. This with the help of the NEPA team. These are the 5-6 areas you see, these we have covered, and how the imaging are covered. So that is the RGB sensor here. And we have, next you will find what is the area cover you can calculate. So generally weed infestation, other things is there. So you can manage how it is increasing, even if you will see maybe eutrophications in the rainy season and increasing the area, all these things. Accordingly, you can have a management plan also, how much weed can be remain, that will not cover during the whole of the rainy season manifestations. Then you come back to the decision support system, or you can give a early warning system to the cooperatives to control this much weeds, or else it will be total infestations. Fish quality, everything will be get affected, and your production also will be affected. Again, these are the, you see, this is a Chamarda wetlands and Chamta is here. So we have calculated the back. We have got total area of these things and macrophyte coverage area. Again, all of you know these water bodies according to wetland authority, maybe 10% will the area coverage will be kept to the weed. But if you see water hyacinth is there, so you should see what is the major things. Again, your classification of the different weeds, and accordingly maybe some of the phytophagous fish or weed controlling fish that can be put into the system that will helpful for the controlling. So these are the some of the things, and you see different terrain, how it is giving area and everything you can go. And this we have come because of a lot of problems comes. Maybe you will see when there is a total, there is no weed. So you are taking a picture, you will find there is a blank is coming also. So that has been worked with the NEPA team from IRA, and we are resolving the issues, and Dr. China Jana is particularly working on this aspect to the developing. Again, if you see water quality parameter estimation and mapping, here is a multispectral imaging water area to estimate the algal bloom, turbidity, chlorophyll A. These are the working we are working in the drone based systems with the how it can come to. So we are in the beginning, we are just a beginning class 1. And we are thinking how best with the help of the NEPA, because they are doing a lot of in this paddy crop, other things. So with their help, we can adventure in this aspect, and that will help for all of you for the, just like you told, na, algal bloom, turbidity, chlorophyll, people I talk about the East Kolkata wetland, that will give a how the management systems will be taken place into this aspect. Again, this is the new aspect here, underwater camera. Underwater drones mostly, camera is not camera we have worked, but say drone we are working for the fish behavior study, feed dispensing study. This is a fungus in our cage we are working. Recently again, we have put a real-time monitoring system with a sensor in cage in Marathon. The data is coming for a DO, but there we are using, but the drawback is here that told that if when moves in a platform gives a noise. So there with that behavior fish is distorted. So we are trying to fix the underwater camera certain place or underwater drone without any noise. Some will come, minimum these things. Again, the another aspect, even if you can monitor the net cage also, how much net cage that has been fouling has been taken place also. Because fouling when sometimes brings the disease of the systems, then we can see how best you can check the fouling, or you can use some of the anti-fouling agents, how many days it remains, or you can have some fish, you can, like we have developed the maybe Rohu model or your Sarana Maran Sarputi model to control the fouling also. The number of fish that can be incorporated, because manually cleaning takes a tedious process. Again, also we are having evening underwater camera utilizing to see some of the behaviors, and we can have the different AI techniques we can extrapolate how can they. Again here, I told these are continuing with this catch monitoring, water turbidity, everything. But there is a constant, I told, turbidity. Again, we are bringing an advanced version under Hirakud Odisha government project, an advanced version of this underwater drones to re-establish and strengthen our facilities also. So that is the process already on. So we'll see how best we can work on this also. Again, I told these are a lot of awareness programs we have initiated, that is under Atari project, or we have the drone project under NEPA project in the different areas, Sundarban, Maina wetlands, East Kolkata wetlands, in the headquarters also. Anywhere we are going, we are just initiating and seeing them. Next. Again, these are the maybe in the different places. West Bengal wetlands we have grown, and also in Bihar when the minister was visited also, honorable minister also. So these are the some demonstration program is going on. Next. Then future scope of work, I told, like you have customizing the drone based water sampling, which will be in a multi-locational sampling in a single fly. different water depth sampling, attaching some multi-parameter probes for real-time parameter estimations, drone-based imaging like this is algal blooms, turbidity, chlorophyll A, estimation using multispectral images, then microphyte species level identification and mapping. Then you will see the spraying and broadcasting also, live water applications, different insecticide application, feed input applications, potassium permanganate. It is not in a liquid form, it's a directly raw in a feed dispenser, which one is directly water soluble, so they directly come to the water bodies that can useful. Again, underwater drone, this is a challenging task because we mostly behavioral study, then migration, feed intake, disease, then identifications. That is more challenging task because of this. That should be, we should put on more focus. Others, maybe with the association with the IRA and other things, we are able to cope up and develop that things. But this is more challenging because we are finding lots. So we should, because underwater taking the image and all things, and we have another work is sonar based also. We have working on this sonar based system by solo fish estimation, how we can integrate with the AI platform also. That we can take over because the sonar based system, imaging system we are having, it was in Bangalore. We brought these things. Last week we brought called the engineer, and we have again we have trial in different places that can be integrated on this project to have the greater things where you error minimization, noise minimizations, and finally that can come into the practice harvest. We can put into the use. And it is not that in a like individual basis, we can have a stock where, because if you large reservoirs, medium, lot of logs are there. Netting process, you have a fishing is a gill netting and other things. So there we can see and advise the people, you can go to this zone for fishing, that fish you can get more fish also. And with this background, I thank you all for patient hearing, and thanks Dr. Sahu and their team coming here and taking this educating the sector for the fisheries, and hope this will have a humble beginning. We are working for last 7 years, it's a humble beginning. Again, this is not that IRA and CIFRI, each individuals, including those are my colleagues here from Arunachal Pradesh and other parts, they are here. We are ready to go to your place, showcase the things with their things, and try to bring you in a platform, is a national platform, because you are all ambassador of this workshop. If we work together, definitely what are the vision of Honorable Prime Minister or the ICAR, what is working for the digital agriculture or precision farming, that will be come into in a real practice. With this background, I thank you all, and special thanks to Dr. Sao and their team who are here from 4th onwards here. Maybe here and bringing the how we'll integrate, because we cannot buy 65 lakhs a multispectral or hyperspectral camera, but we can bring them for studying something, building a concept. Later we can somewhere put that we can do the things in a magnanimous manner for other parts of the things. So that's the whole thing, and that's because we brought all of you. You take the message and we can work together. Thank you, Aiga. Thank you.
Thank you, sir, for a nice presentation and the kind of accomplishment with a very short time. I think CIFRI is going to take lead in the country with respect to drone in fishery. Number of applications as you have gone through, and we will be always happy to work with you, my team, and also NEPA team from fishery institutes and others. Since we have a committee on drone for multitasking, I think some of those examples what you have talked about, we could see that happens also practically in the field. Before going for my presentations, I would ask if participants any question, anything you have online or offline. Anybody from here? Any question? Any concern you want to? Because this is not only training, this is a kind of workshop. Any comment, any critical input will be very useful for all of us, and it's everyone is a part of this purpose, drone for agriculture. So, any comment, any observations? Sir.
Restriction from DGCA side regarding the payload which you can handle with the drone, because as Dr. Das was referring to having a 100 kg payload to be used for transportation. When more of such drone will fly in the fly zone, there has to be some flight controller regulator, because otherwise in the traffic, more the traffic, then it is to be regulated as you do in the flying zone. So is there any restriction? I just wanted to know, or we can go for that.
If you go to DGCA site, there is a guideline which is available with respect to classification of drones. Again, because of the time constraint, all those basics we are not going to cover. Mini, micro, macro drone based on the weight, carrying weight. Same also for the pesticide drones. There should be less than 25 kg for which you can get the pilot license. If it is more than 25 kg or 50 kg, for that you have to again go for pilot licensing and clearances. So DGCA needs to approve drones with the different payloads for that purpose. And also the person who is doing that mission, he needs also that capability of driving, like I can drive a truck, I can drive a train. I need a license for that purpose. Same also in case of DGCA. So there are already set rules and regulations for that purpose. Anybody? Please be free. Any vague question also can be asked. Doesn't matter. This question is not relevant, nothing like that. But related to what Sir was talking about, because all are from, many of you are from fishery science, and so if you want to ask, because I just asked Sir to do so that being the director, he has a lot of responsibility to take up. So, and we are already 1 hour late for that purpose. So, but I'll try to finish as early as possible. Just try to pass through. If time permits, maybe I can make a presentation again sometimes later of the evening, because my team is waiting to go for a live demonstration. Before that, they have to take the class, and we have a lunch time. So already 12:20, I think now. Yeah. So let me finish by, if Sir permits, maybe by 12:45, if I can do that. And 15 minutes, you people can take here, the engineer Purushothaman and engineer, the team. 15 minutes, just an overall, quick overall. Then we can go for live demo 1 to 1:30 or 2 o'clock. Then 2 o'clock, we can break for lunch if everyone is not hungry till that time. 1 hour late we are. So I'll be talking on just taking you through the drone technology, recent advances, and the way forward. And myself, Ravi, and Sahu, working with IRI almost more than 25 years now. And again, being a student of IRI also, again from Agents of Physics, where we started long back, 1969, fast airborne remote sensing in coconut plantations in Kerala. So that's the department where all basic strategic research we do related to remote sensing. And since quite some time, more than 5 decades. And you know, all IRE, but many people who are not from ICAR systems or NAS system, you know, IRE is a building system for many technologies with respect to crop, soil, or sensor, anything. So this is again another technology where we do a lot of basic and strategic research. And the left-hand side, the field, what you are looking at, see is the IRE experimental field of Nepal, where we have grown different experiments with the different variations to capture using different sensors. And top one is the most expensive drone with the expensive camera. That's what given by Electrotech International from Headwork Photonics from US. The camera cost me around 4.5 crores. And the drone has automation kind of anything goes wrong. You have an airbag. You will just fold out all the sensor all around. So if it is a free fall, nothing will happen to the sensor. And the down one is the spraying drone. So that is for high-voltage applications where you require. So that is the sensor for the monitoring of the crop. The top one, it can monitor any kind of parameter you are looking at. Just I'll take you through. I won't talk much of science behind it. And down one is a 16-liter tank where you can put pesticide, you can put liquid area, or anything you want to, you can
Sir,
go.
whose side, sir?
So coming back to the drone technology, I was talking about drone is for the two purposes. One is for the drone. If at all you can integrate the sensors, and if you can integrate the sensors and think you have minimized that one. Yeah. Yeah. So that is for the crop monitoring, discrimination, crop health monitoring, soil health monitoring, phenotyping, any kind of things you want to do by using sensing, different sensors, you can do that. Then drone as a applicator, like herbicide, liquid fertilizer, bombing of the seeds, like afforestations you want to do in forest department, they do a lot. And broadcasting of fertilizer, broadcasting of seeds, broadcasting of the feed, fish feed you can do, cargo and many other purposes that can be used for. And why at all drone technology? We have a satellite remote sensing. Satellite since long it is we have, but how come drone has come up with, to the picture? The purpose is drone is more of a user friendly and user requirement wise it meets all the requirement, whereas satellite doesn't do that. Like satellite has a fixed time of flying, fixed time of fixed sensor, fixed height, fixed resolution, everything is fixed. One satellite is launched, crores of rupees you spend on that. And if it is cloudy, the gun, then you have to wait for some other day to come back. So everything is fixed. In case of drone, it's a kind of plug in, plug out. You fly as per your requirement whenever it is bright sunshine or good conditions, and you can put any sensor you like to, any height you want to fly. So all that purpose, drone is going to meet that requirement. But the challenge remains is satellite, everything is fixed. So data acquisition, data processing is very easy, very routine exercise. In case of drone, starting from flying to image acquisition to processing is a bit complex unless until you are trained, you are expert, it's not going to be possible. So that's what the disadvantage is. Another disadvantage is satellite can cover larger area, is a large synaptic view. In case of drone, it's only limited area. For example, whole Ganges you want to monitor, starting from Himalaya to down to the West Bengal, it's not possible by the drone. You need a millions, maybe hundreds of drones to fly and get it done. But in case of satellite, you have a satellite which flies with a swath of 10 kilometer to 800 kilometer. That's what the swath, the kind of area coverage, resolution starting from 30 centimeter to 8 kilometer, 1 pixel size. So that kind of capability what satellite is having. Within no time, whole India you can monitor. We have a satellite at our receiving stations where pan India we monitor the crop conditions itself. In ICAR itself we have that. So these are some of those pros and cons, but drone is in between. Whatever the challenges you have in the ground, whatever the challenges you have in the satellite, drone meets that requirement. So that's the reason wherever you have a challenges, you are not able to solve the problem from satellite, you can do by drone remote sensing. Drone remote sensing, because drone based, you put the sensor and do the remote imaging and information retrieval. That's why we call it drone remote sensing. So these are different sensors, what is available in the market, starting from RGB, thermal, multispectral, hyperspectral, and LiDAR. I think my team is going to take you afternoon. All those sensors we have available right now outside, you can see and interact with the team to know all about detail about that. So again, I'm not showing all those movie files because of the time constraint. So this is the right hand side is the 2016 and this is 2020. So that was the first before Prime Minister's demonstration. We have a dry launch, and 2020 again, this is a hyperspectral camera. After 4 years, we developed that. And this is what I was talking to IRE since 1969. First time airborne campaigning was happening, 1969. Many of you might not have born by that time. So almost more than 50 years, that's what the airborne campaign was there, UAV. But the UAV or the flight was borrowed, sensor was borrowed. Now we have again 2019, we have everything on our board. Like many startups are there who are having their own in the drones, and also we are having the sensors we can integrate and fly. And you can see the 2018, again, we have a very ambitious program with JPL NASA, airborne campaign we did. What I mean to say is we have been working with the time of the last 5 decades, many advances in the sensor technology for the soil and crop health monitoring and also many purpose. And these are the capability over the time we have developed in IRA, starting from very low cost sensors of 10,000 to 4.5 crores. That's what the sensors what we have. I think this is one of the best facility in the world, even if having that all kind of capability at a go. You go to the lab, you will see everything available with us. And you have a drone starting from a flying and landing on your palm, and you have a drone with carrying up a 10 kg payload and fly all around. And these are the labs what we have. Couple of labs we have developed over the time for the hyperspectral lab, drone remote sensing lab, big data analytics lab, Phenomics Center. I think many of you might have visited IRE, and always you are welcome to see and come back and see how we do all those things. So this is how the sensing of the laboratory to field scale, we do capture the data starting from lab conditions to the field conditions. So before going to the satellite, always we do in the lab conditions, having the same sensors we have on a robot where it moves, capture the data in the field, robot mobile platform as I see you in the right-hand side. Then same we fly on the drone with the same sensors, finally we do with the satellite. So starting from a lab conditions to large scale, we do all that kind of capability. Of course, they have their own limitations. Coming back to the crop and soil, since we are more into that, where we little know about the fishery and aquaculture, but I'll cover some of those basic principles. So these are the cameras which is available, and you can fly in the field. Within no time, you get these color images to indicate where the crop health conditions, how it varies with respect to different crop health attribute. And these are the different cameras, what multispectral, RGB and hyperspectral cameras. It's like you have a mobile phone, or you can look back 50 years back, the story, the movie file, panchromatic black and white movies were there. Then we had black and white Konark TV or something like that. Now, over the time, Onida and many other things, Sony Bravia came out. Then we have a color movie with a good LED with contrast. So see the differences. If it's black and white, you can see somebody standing there, but who is that? What kind of color you don't know. But if you have RGB, you come to know. But if you have a hyperspectral, again within that color, what the variations you can capture? You can capture all the quality. So that's what the hyperspectral stands for. So when you look at the plant, you can see the plant, how it is behaving. Like you have a thermal image, a black and white image, you can know whether this is a wheat crop or a maize crop. That's all you can do. But whether this plant and another field plant, how they're behaving with respect to nitrogen stress, with respect to pest and disease, using multispectral also to some extent not possible. So this is the camera, like kind of PET scanning. You go to a hospital, you do X-ray scanning, you do ultrasound and do MRI. Nowadays, MRI is becoming common because easy to diagnose what's happening where. That detailed information you are able to get. Same also in case of remote sensing. I'm a radiologist for that purpose. So you look at the simply RGB camera, look at the multispectral camera, which has 5 bands. Where you look at hyperspectral, you have a large number of channels. You can see the right-hand side, what I have displayed there. Here, you can see this is a 3 bands, there are 5 bands, and this is continuously you have bands. That means each part of the spectrum is interacting with the plant with respect to biochemical, biophysical properties, and that's what the variations, and you can capture all those properties for that purpose. Then again, this is what the sensing system, as I was saying, we have a control conditions where you have all kind of the sensors. You have in field in the drone and also mobile platform capturing soil and crop conditions for different purposes. Purpose is high throughput phenotyping, precision agriculture, crop health monitoring, pest and disease, all those purposes we are trying to do. And these are all big data analytics we try to use with respect to machine learning, deep learning, and also generative AI. I think some of those things my colleague they're going to talk about. So coming back to, this is what the in-house developed software, which you fly the drone, within no time you can get the map generated. You don't need to understand how to do all about that. So this is almost a user GUI-driven software, which in-house we developed. Commercial softwares, whatever available for the drone data processing, that is only pre-processing, coming back with the image. But beyond that, creating except indices, nothing it does. But here, you can create a thematic product directly. You put the data onto the software, process it, get to the thematic product like chlorophyll, LI, all those things. Let me take you around that. These are all possible applications of drone technologies. So I think many of you must be knowing all those things, starting from monitoring of the crop health to the yield estimations, damage assessment, and also for the crop insurance purpose. Drone is one of the key parameter which has been used globally, and also India. There are a policy document which is available for that purpose. Coming back to few applications, quickly I'm rushing because of the time constraint. Sorry for that. I have again 10 minutes only. So look at the soil fertility. You see, we have a sensor. This is what most expensive sensor again in the field. Going on the back, you can put and go for the collecting the data starting from 400 to 2500. This is what the spectral signatures we are getting. Same time, we have a hyperspectral camera just lying outside in the integrated with the drone. You can see this is what the engineer Purushothaman has given to us. Again, this camera cost me something around 60 to 70 lakhs, 400 to 1000 nanometer, having 270 channels. And this camera cost me, as I showed, 4.5 crores. It has around 600 channels at a time. So you can see the kind of spectra what you are able to get. And these are the two satellites from Europe. One is Germany, one from Italy. We, again, same field we are looking at. So these are the soil sampling, which is done 5-meter grid scale, and this is 100-meter grid scale of whole IRA. And we are trying to see how best we can characterize them with respect to soil fertility. This is what the organic map generated out of those from the ground and also from the satellite and from drone, what you can do. So this is what the possibility behind a lot of science coaching with respect to deep learning. What are the challenges we have? So those things we can discuss again further. This is what the airborne campaign, which we had around 3 to 8 kilometer height. See, this is what the Raichur area. So you have a drone image, the kind of airborne imaging. This is what the flight on which the sensor has gone. This sensor is 100 kg payload. And this is an airborne campaign. This is a flight of an RSC wherein it integrated, and engineer from NASA and from pilot from India, they have been there. We are the science team camping here. So you can see the raw data, how it looks like. This is Raichur sheet producing farm. And this is the organic carbon map, which you can generate. So this is how quickly you can do. This is what 2016, again, with these are DTU students here. And you can see this is Professor Raghav. This is Dr. Pawan Agrawal. That time, Dr. Honorable DG Ayapan sir was asking if at all we can give a fund. That's what the ITER project was supposed to be on Sensagri. So he's the ADG NS at that time. So he came to witness what the kind of technology we are developing. This is a fixed wing drone. You have a drone, quadcopters, like you see, whatever, though they can just take a vertical and landing vertical, but this is kind of helicopter and flight, you know, the kind of difference, same difference here. Again, I'm not talking more. So within no time, whole IRE field could be captured, maybe another 10 to 15 minutes flying this fixed wing drone, and you can go for mapping. So these fixed wing drones are very quickly can cover large area and go for the mapping, but there are a lot of challenges for that purpose. Coming back to some of those applications, flying the drone with the RGB camera, you can get the chlorophyll estimation, you can do the LI estimations. These are some of those, you can go to the research gate, see all those papers are published. And this is what, once you drone fly on the maize crop, you are able to count down the tassels there, cobs there. So this is what so usually what happens is the plant scientist, the breeder or plant physiologist, they go to field, capture and count them, but you don't need to do that. This is what the ELO technique by which you can capture within no time how many tassels are there, how many cobs are there. So now the most advanced is number of panicles, number of leaf tips, everything we are trying to do using latest computer vision technique for that purpose. This is how the drone image is captured. You can see the frame wise is the frame grabber kind of thing. The image is captured like you do the photography. And this is the oldest camera of Mikasense, which is the drone camera Gojin. There are 5 bands there. So this is what IRE found. Each dot is the image which is captured. And this is what wrapped over the Google Earth image to see the expanded field what we have. And this is what the field with the differential treatment of the water and nitrogen. D stands for drought, N stands for nitrogen. You are able to see the difference. D and I is irrigated and drought. And N0 is no nitrogen, N120 is sufficient nitrogen. And you are able to see on the right-hand side that color image. So you derived this data was captured, processed, and you got a color image like this to tell you how the plant is behaving with respect to those treatments. And also each subplot has around 7 plant types. So how they are differing, this is what the layout given on the right-hand side. This is what within no time you will be able to capture. So you think of going to the field and capturing the data, how much time it takes. This is all done by 5 to 7 minutes time. You can do everything like this. Not only that, stage-wise also you can monitor how they are behaving in the field with respect to their phenostages, critical growth stages, and also each field, as I say, 7 genotypes were there. Around 29 genotypes, their heat map has been generated. Ranking has been done. Which genotype, phenotype is working good. So the people who are into genomics, you do the field phenotyping, you do fish phenotyping or plant phenotyping, you do the genomics. Before going to genomics, this is what the phenomics you can do. You can prepare a heat map. You go 1,000 plant types, and within no time, you can get all the attribute you require and go for ranking with respect to selections, what you want to do. Coming back to thermal imaging, this is what the field where you have a thermal imaging camera just scanned through. You are able to see the canopy temperature map of the field. Within no time, you are able to see the water stress. One side of the field, which is bluish, these are the sufficiently irrigated conditions, whereas the right-hand side, which are the red, those are the water stress conditions. Temperature is high. So temperature is high because there is no more evaporation or transpiration. There is no water available for that purpose. The plant is under stress. Or maybe the genotype is not, they're very susceptible, so you got evaporation loss. So that's what the differential response you are able to see. Which part of the field you can go for irrigation, which doesn't. So this is what we can do with the thermal camera. Most of the time we do by thermal camera flying over a grapevine or over any plantation crop or any crop, for not only for irrigation shielding or water requirement, also pest and disease monitoring. This is what the biomass estimation of the field. This is a rice field, and sometimes in October the image was taken. This is a very low cost technology like RGB, and we created some image derived some indicator and developed the yield map of the whole field of rice biomass, which we could do, and using drought and control and nitrogen conditions. So you are able to see the variability which you could do before harvest. You can do the yield mapping and also biomass estimations. I think I should skip this slide. This is around 10,000 rice land races which is grown in the IRE farm. If you think of physically going to each field and capturing any data, 10,000, how much time it would take? So it's a 5 minutes fly over the area, and within no time you can have a virtual feeling of how the field is behaving. This is what the 3D simulation model, which was done simply from RGB drone flying over there. You are able to see the gaps where it is, how the germination is, how good or bad. Not only that, you can get also height estimations from this. So this is what the 10,000 land races you can do phenotyping or the attribute mapping within no time. So you can think of how much money, how much energy has been saved by that time with respect to accuracy. And this is a centimeter level accuracy what you can get, because drone is flying something around 20 to 30 meter height only. So this is what the capability what you have. Then coming back to the latest sensor, what hyperspectral we do in number of crops like rice, wheat, maize, mustard, and all those things. And this is what the wheat field with the 8 nitrogen treatment, 3 irrigations. You can see the color map tells you how the nitrogen mapping is done with the node. And this is raw image. This is a nitrogen map of that field. So you're able to see the nitrogen variations in the field. So from raw, you got a thematic nitrogen map generated out of it. So you can go now where the nitrogen to be applied, where not to be applied. So this is the field where you should go for the nitrogen dose applications. Here, you may not be. Again, there is a color mapping is done with respect to nitrogen content. As an expert, you know how much is the leaf nitrogen should be to be applied, how much fertilizer to be applied. So based on that, you can not only go for off and on of the drone spraying, also you can do the rate of variations, rate of applications also you can vary. This is what the technology one has to use for the variable rate applications. So coming back to another experiment, for example, this is what the all machine learning models left-hand side you are able to see. These are the biophysical product which you can generate. Once you fly over the field, within no time you get LI, leaf area index. You can get a canopy chlorophyll content, CCC. You can get also CNC, canopy nitrogen content. So this is what the product generated. So you don't need to understand the science behind it, how it does, and all those things. That's what the machine learning models are doing. All are calibrated and validated. Everything is going to be put into that software where you can do everything automatically. So these are the products generated: leaf area index, canopy chlorophyll content, nitrogen content, and also grain yield. So before harvest, you are able to estimate all those things. Again, doing all kind of a data acquisitions, processing, using machine learning and also physical process-based model. Again, I'm not going to talk more detail of that. If anybody is keen interest, we can talk in detail of that. So this is what the yield mapping you are able to do within no time. So field-wise, you are able to see the variations with respect to the content, that attribute, maybe chlorophyll or nitrogen. Even you also yield mapping, you are able to do that. So same thing we are trying to do in a larger area, like using the satellite. This is what the satellite of whole IRE farm for the soil, for the crop health monitoring and also soil moisture. And same thing we try to do also the larger in the Karnal district we have done from the satellite, not from the drone, from the satellite. So starting from the lab conditions to the drone conditions to satellite level, we will be doing to make it a scale neutral, and you can go for the monitoring, provided you have done all those success stories in your controlled experimental field. So that's the purpose where the drone is working. Coming back to the pest and disease, these are a couple of pest and disease monitoring we have done using different sensors, including multispectral, hyperspectral. For that purpose, you can see one of the example is yellow rust in case of wheat. This is what we have done with the hyperspectral, and this is what the average NC campaign where red dots are the hotspot where yellow rust was there, infected the wheat field in some of the northwest part of the country. This is what the students, my team which involved, flying the drone in the field, going for the BPH of rice, wheat aphid, rice blast, all those diseases we are able to do. Again, just an exposure to see how we do all those things. So this is a field, again, flying a hyperspectral sensor over the field with the differential treatment. You click on any pixel, you will get a spectra like this, and you are able to see how the N0 is behaving, how the N60 is behaving, how N120. And this data is the huge knowledge it has in between. You can capture all possible attribute out of that. So I'm not covering those parts. Again, I think I should skip all these things because of the time constraint. One of the important is whether you can go for discrimination of different genotypes, different varieties, or different crop types. That's possible. This is what the 29 basmati, non-basmati varieties were grown in the field. Flying the drone and discriminating them, you are able to see the discrimination. This is what the ICAR is famous for basmati. So we have a long-term experience for that purpose. So this is what the basmati, non-basmati differentiation we are able to do. That's what the capability of hyperspectral. And these are all aromatic, non-aromatic, all those possible applications you can do. Most interesting part is crop height estimation also. Within no time, you can do crop height estimations simply using RGB. We have another sensor called LiDAR. Crop height for today and tomorrow and day after, you can go for monitoring, or a week wise, you can go for monitoring. Based on the crop height, you can go for biomass estimations, also field phenotyping. So these are all possible applications. This is what the grapevine with the Mahindra and Mahindra, we have done pest and disease monitoring and also disease, also nutrient stress monitoring. This is for the coconut, unreachable areas where you can fly something around more than 50-meter height, capturing different coconut plantations and also the pest and disease attack on those. So, and this is again a northeast part over the Ceylon, very hilly terrain where we have flown the drone to capture those forest species and to characterize them, which forest species is good for the carbon sequestration, carbon stock. That's what the World Bank funded project. This is what the left hand side you are able to see on the hilltop on Ceylon. We are flying and capturing the very risk. This is what my team there we are flying. So again, monitoring the agroforestry, we are able to do that also close by Delhi regions that we could do. So coming back to a very interesting movie file, again, time is around quick file. So this is what the orange plant, you can go for counting, flying the drone all around and get estimations of yield estimation within no time. So this is what my team from CI Gopal, they have done these exercises. They have developed the app also. So within no time on your mobile, once drone is flown, you can know each plant how much yield has come with respect to orange. Same also with mango and other things you can do. So this is behind simply low-cost camera, but RGB computer vision based programming has been done for yield estimations. So this is a
पक्षी के
technology for the drone.
द्वारा चलित ड्रोन्स का उपयोग अब कृषि के क्षेत्र में भी स्मार्ट कृषि को बढ़ावा देने के लिए किया जा रहा है, जिसका सीधा लाभ छोटे और मार्जिनल किसानों को मिल रहा है। भारतीय कृषि अनुसंधान संस्थान ICAR के कृषि भौतिक संभाग द्वारा विकसित ड्रोन अर्थात अनमैन्ड एरियल व्हीकल का प्रयोग काफी कम लागत में बहुत महत्वपूर्ण जानकारियां उपलब्ध कराता है, जैसे कि हाई स्पेशल रेजोल्यूशन इमेजिंग, रियल टाइम इंफॉर्मेशन, अनलाइक टू सैटेलाइट टेक्नोलॉजी, फ्लाइंग हाई, टाइमिंग और यूज ऑफ सेंसर की फ्लेक्सिबिलिटी के चलते ड्रोन बेहद उपयोगी उपकरण है। RGB, थर्मल, मल्टीस्पेक्ट्रल, हाइपरस्पेक्ट्रल जैसे सेंसर्स का प्रयोग करके आर्टिफिशियल इंटेलिजेंस टेक्नोलॉजी की मदद से किसान सफलतापूर्वक फसल के स्वास्थ्य की रियल टाइम मॉनिटरिंग कर सकते हैं और आसानी से पता लगा सकते हैं कि फसल को कब और कहां फर्टिलाइजर, सिंचाई या पेस्टिसाइड की जरूरत है। इसके अलावा मवेशियों और फ्रूट क्रॉप की मॉनिटरिंग और उनको नुकसान पहुंचाने वाली संभावित बीमारियों को भी ड्रोन के सेंसर से पूर्वानुमान किया जा सकता है। कृषि की उत्पादकता और रूरल इकोनॉमी में आधुनिक डिजिटल टेक्नोलॉजी, विशेषतः ड्रोन, एक महत्वपूर्ण भूमिका निभा रहा है। आज नए भारत के किसान की समृद्धि का भरोसेमंद हम सफर है ड्रोन।
This is a small clip for that purpose. I think I should skip this. Dr. Rajiv is going to talk more about the drone-based imaging and spraying. This is somewhere in the rice field we did. I'm skipping this. Coming back to little bit, just whatever little knowledge we have with respect to water quality through drone sensing. These are all, let me take you, these are the different sensors which is available for water quality monitoring. You can see the kind of publication technology. That's what coming out with the scope citations. And let me come back directly to the side. This is what the instrument hyperspectral data you can capture. And these are the different wavelengths for the purpose what you are looking at, like chlorophyll, like colored dissolved organic matter, TSS, turbidity. Already the defined wavelength ranges are there. If at all use those camera which is outside lying right now, you can do all those mapping for that purpose. You can look at, this is what the different wetlands which can be mapped within no time using those visibles 400 to 900 spectrum. You can go for mapping and quantifying them also. This is what before we visited to SIFA and SIFRI, we did a home exercise, my team. This is what our Amrit server in IRE farm, we have flown the hyperspectral camera and multispectral camera. This is what the field is where you are able to see algal growth over there with the different sensors. You can see this is what that was the multispectral sensor having only 5 bands. We are able to see, and this is what the water body, red one is the water body. This is what the algal growth, what it happens. So same also in case of hyperspectral, you can see, look at the soil, how they look like, how the algae looks like, how the vegetations look like, how the water body looks like. So within no time, you can map where are those algal growths and how much and all chlorophyll content. And based on the algal growth, based on the chlorophyll, phytoplankton, you can go for the indirectly modeling of dissolved oxygen. So this is what indirectly people have been doing, dissolved oxygen monitoring for that purpose. This is what the, again, SIFA farm, which was done December 1, only 10 days back, we could do that, and corresponding parameter has been there. I think PC Das Purna is here, who from, yes, he has collected all those data. So these are the different ponds with the different phytoplankton, different parameters. Within no time, you see the hyperspectral data captured, the pond 1, pond 2, pond 3, pond 4, and these are the different attributes. We are trying to map that. We have not got much time since then we are traveling, but still you can see the initial results, what is there. This is what Dr. Das already has shown you, how they are doing in the different areas in presence of direction of China and my team. And this is what the same hyperspectral from the satellite. This is a Prisma Italy. We try to Chamta and Chamarda. These are the different data which has been captured from those sites, and going for the TDS and pH monitoring and regressing those models. So not only that, from the drone you can do similar sensors you have on the satellite. We are trying to do so that large scale monitoring you can do for that purpose. So this is what the algal growth using the spectra for those water bodies you can do. This is what the average NG campaign. My team from NISA, I had another bigger program with 37 centers, DST funded program. I was the program leader for that. Again, many IITs were involved, IIT Madras, IIT Kharagpur. There are two who are doing the science campaign in the Hooghly River when the NASA jet was flying over here. So this is Hooghly River. You can see these points where they are able to capture the spectral signatures, that is called inherent optical properties, apparent optical properties, from which you can characterize how the water bodies, what are the qualities. So this is what the Haldia River and Hooghly River, this is what the data has been captured. Lot of work you can do. This is coming back to the future. As I was talking, 5G technology. This is what the 5G technology captive network you can integrate on a drone. And this is what inaugurated by Honorable Prime Minister virtually, that lab. This is what the 5G lab, what we have. And this is what technology, what we are demonstrating. This is what the future. If you have a 5G captive network, so whatever the sensors you have, that are 5G enabled, then automatically they can be captured. The soil moisture, canopy environment can be captured, coming back to your screen. And you can go for actuating irrigations by the drip or by fertilizer applications. That's what the capability what we have. And this is what swarm drone technique, as today morning I was talking of, same taking the swarm concept. Using the 5G technology, you can fly 100 or 200 drones within no time and capture all possible data for that purpose. This is what the IRE farm. You are able to see these drones flying all around. You have a mother drone where you have a edge computing device. Within no time, it can capture the data, process those data. This kind of a mobile server where it can process, and that can actuate a command where what irrigation has to be done, what intervention has to be done. So this is what the kind of possibility what we try to do. Same time also you are flying, like there are different drone companies which are called 5G enabled drones. So where his drones is flying in the country, pan-India, you can do. For example, other day Pratim was talking, sir, when you go beyond 100 meters from here, my drone is not able to fly beyond 20-meter height, 30-meter height, because there is a jam given by the Barakpur Kant area. So always, if at all your drones are 5G enabled, those sensors that they can detect where the which drones are flying with respect to the frequencies, and you can monitor whether this is right now in the active mission or the lying idea. So these are some of those key questions for drone in agriculture to complement with the satellite, not to replace, and how best we can use this drone technology for different applications of agriculture. That's what the concern is. And we are here to see how drone technology can be for precision agriculture. These are the different demonstrations, all delegations all around the world, including Bill Gates, many committees, all were here, governor of UP, many minister, parliamentary committee, anybody comes to Delhi, they comes to us to see how the technology is. I have a big team. It's not an individual. That's why I have written Ravi et al. Is the publication, the presentation. So some very active team is sitting here, Dr. Amrita, Dr. Reji, Dr. Raji, Pratim, and of course, Purushottaman, who is here. You can see the pictures. He's there throughout all the way. So we are joining together. So this is what the website where you can go and see more detail of the program, what we have, network program, Precision Agriculture NEPA. And thank you very much. So I think if at all there is question, maybe on the lunch break we can do, or people can put on the chat the questions because we are running out of time. Again, I have enclosed around 10 minutes more, though I rush like anything. I request both the engineers, pilot, and the experts to come and have a brief talk or presentation, whatever you want. If you at all can go to the field. Is it okay? Yes.
Thank you, sir. Thank you for giving me this opportunity. And I'm really thankful to our Honorable Director, sir, our program leader, Dr. Arun Sahu, sir, China Madam, Rajiv Ranjan, sir, and all other respected guests present here. especially from last 2 years, whenever I come here, Director Sir, China Madam, and our Kausikda is like umbrella over my head. Because of them, we are getting the data of wetland. So thanks for your support and blessings. Wish you warm welcome to the world of unmanned aviation. Here I will cover the basics of drones, their different types, their flight principle, and some overview about the components inside the drone. So, as per the Drone Law 2021, the Director General of Civil Aviation mentioned the drone as Remotely Piloted Aircraft System or RPAS. The RPAS is sometimes referred as Unmanned Aerial System. So, the UAS or Unmanned Aerial System has two components. First one is the UAV or the Unmanned Aerial Vehicle, which we fly in the air. And the second one is our Ground Control Station or GCS, which we use to control the UAV. Now, the flight principle comes from the Bernoulli's principle. As per the Bernoulli's principle, whenever there is an increase in velocity of the fluid, the pressure decreases and vice versa. That means whenever the speed of a flowing fluid or any air increases, the pressure decreases. Depending upon this Bernoulli's principle, engineers developed a specially shaped object that is called airfoil or aerofoil. It's nothing but the cross-sectional area of an aeroplane wing or the cross-sectional area of a propeller. So, when there is a relative velocity with the wind, as you can see here in this image, the high velocity air comes from the forward portion, gets divided into two different sections. The upper portion of air travels from the upper side, has a higher velocity compared to the lower portion air. Due to this high velocity, this area has less pressure compared to the lower area. So due to this difference in pressure, a force comes into play that is called lift force, and our flying machines airborne. So drones can be categorized into three different types. First one is the rotary wing, second one fixed wing, and the third is hybrid. So as from the name, fixed wing, that means there is a wing that is fixed over the aircraft. It cannot move or rotate. Whenever there is a relative velocity with the surrounding air, the wing generates lift force, depends on Bernoulli's principle, and our machine can fly. Now, the fixed wing drone uses certain control surfaces or certain objects. They are called elevator, aileron, and rudder. So whenever these objects are moved in different angles, the drone can take turn, go up and down. So there is a comparison between advantages and disadvantages of different drones. As we can see, the fixed wing drone is not VTOL. That means it cannot perform a vertical takeoff and landing. It needs a proper runway to get the necessary speed for takeoff. But the benefit is it has a very high endurance, can cover large area, and flight speed is more. So if we concentrate on the hybrid UAV, as from the name hybrid, that means it has features of both fixed wing as well as rotary wing. So you can see in the first image, there are 4 lifting motors placed like a conventional quadcopter. So it generates necessary lift force for takeoff. That means to perform a vertical takeoff. Whenever it attains a certain height, then the pusher motor starts, and with the help of the wing, it flies like an aeroplane. So it can glide in the air like a fixed wing, as well as it can perform vertical takeoff and landing. But the disadvantage is they are very expensive, design is complex, and needs a lot of training for flight. Then comes the rotary wing UAV or rotorcraft. Now, rotorcrafts are again classified into 2 different types. One is helicopter and the second one is multi-rotor. I will not cover the helicopter part because this presentation will be very long. I will concentrate on multi-rotors only. Now, as from the name multi-rotor, that means there are multiple rotor blades which rotates at a certain speed to generate necessary thrust force for flight. Now, multi-rotors can be classified depending upon their number of rotor blades. So there may be a tricopter having 3 propellers, maybe quadcopter having 4, hexa having 6, octa, and many more. So now if we concentrate on the controls of drone, all the drones has two parameters for control during flight. First one is the attitude and the second one is called heading. Now the attitude part has two components. One is the roll and pitch. Roll means rotation of the aircraft with respect to the x-axis, and pitch is the rotation of the aircraft with respect to the y-axis, and yaw means rotation with respect to z-axis, and our heading is the angle with respect to Earth's magnetic north. Now, here you can see these are the diagram of remote controller, or which we call ground control station, to control the flight. So it has two sticks for control. The right hand stick is used for roll and pitch movement of the aircraft. Left hand is used for throttle, that means to control the altitude, and also the yaw or rotation of the aircraft. Now, here you can see 4 images of those two control sticks. The first 3 images are of throttle. So whenever our throttle is at 0% or full down position, drone is on the ground. Whenever it is at 50% or half, our drone can hover at a place. Whenever it is more than 50, going near the 100, then our drone starts going up. And the right hand side image is the control stick. When it is in center, drone perform no pitch and roll. It's hover at a place. Whenever we push it forward, backward, left, right, our drone perform attitude. Now, in this slide, we can see 4 different images showing us what happens when a drone takes off. In the first image, our drone is on the ground, so gravity is working vertically downward. It cannot fly now. In the second image, whenever we arm the drone or we start rotating the propeller, the thrust force comes into play, but till it is on the ground, because now thrust is less than the weight. In the third image, when we push the throttle up, our thrust force increases compared to the gravitational pull. So our drone starts going up. And in the fourth image, when the drone hovers, that time thrust and weight gets exactly equal. So we can achieve a hovering in the air. Now, in the forward, backward, or the pitch movement, suppose we have a quadcopter and we want to make it forward. So the motors mounted on the back section of the drone, speed increases and the forward portion motor speed decreases. Due to this, our drone tilts at an angle and it gets a force. So due to this force, our drone starts going forward. Whenever we release the stick, again all motor speed gets equal and it starts hovering at a place. In case of left-right movement also, whenever we want to send it at left direction, the right side motor speed increases and the left side speed decreases. Due to this, there is a tilt and again it starts going in that direction. Now, to achieve the circular rotation or the yaw movement, the motors mounted diagonally can be controlled. The speed of the motors are varied in diagonally, so our drone gets a torque and it starts rotating. Whenever we release the stick, all 4 motor RPM gets equal and again the drone hovers at that position. Now, there is a relation between the Newton's third law and drone flight. So as per the Newton's third law, whenever there is an action, there will be an equal and opposite reaction. So when our motor gives a clockwise torque on the propeller also gives a counterclockwise torque on the motor. So due to this, if all 4 motors rotate in clockwise direction, our drone will start rotating in counterclockwise direction. So to overcome this problem, 2 motors are rotated in clockwise direction, rest of the 2 motors rotated in counterclockwise direction. So our reaction torque can be 0 and we get a stable flight. Now, if we concentrate on the components inside a drone, then there will be 5 different type of components. The first one is the power, which has our power source, that means the battery, our charger, our power distribution board, and many other components. Second one is the propulsion, that has our motor, propeller, speed drivers. Third one is the navigation, which has our GPS module and electronic compass. The fourth one is the inertia measurement unit, that has one IMU, flight controller, and the last one is command and control. So I will give a little idea about these components. First, the power portion has our power source. Lithium batteries are used in the drones as a main power source because lithium has very high energy density. So we can store a lot of energy into a very small and lightweight component. So most of the time, lithium polymer or lithium ion battery is used. I will not cover the battery part in detail. Then there are many parameters related to battery like capacity, number of cell, discharge rate. Depending upon these parameters, the flight time of the drone depends. Now, the most important thing related to lithium battery is the LiPo battery hazard. As we know, lithium is highly reactive with the oxygen. So whenever a battery cell is punctured or damaged, it may cause explosion, fire, or catastrophic disaster. So we have to be very careful while handling with the lithium battery. We should not do overcharging or over discharging with the batteries. Now there are other components in the power part also. That is, one power module is placed inside. The power module takes power from the battery and supplies it to the brain of the drone, that is the flight controller. Also, there is a power distribution board which distributes the power into different voltage levels to different components. As you can see, the black one is the power distribution board. It is written as PDV there. And also, there is a converter which converts the voltage from the main battery at different voltage levels to run different accessories. So this is the internal circuit diagram of the power portion of the drone. The power is coming from the battery, going to power distribution board, then it is supplied to different motors, and also same time it is supplied to our accessories at different voltage level with the help of voltage converter. Now, if we concentrate on the propulsion system of a drone, the first important component is our motor. Now, BLDC or brushless DC motors are used in the drone because they gives us precise speed control. At the same time, they have less wear and tear compared to the brushed DC motors. Now, in case of BLDC motors, the permanent magnets are placed at the rotor part of the motor that can rotate, and the electromagnet is placed at the stator part of the motor. You can see in the first image. So whenever the coil or the electromagnet is energized, our permanent magnet rotor experiences a magnetic force and it starts rotating at a very high speed. The speed can be controlled with the help of these tiny electronic switching devices called electronic speed controllers or ESCs. Now, ESC has different specification depending upon the size of the drone, the type of the drone, and many other parameters. So due to this different specification, different firmwares are developed for these ESCs. I will not cover this part in detail because it will be very long. So the last component of the propulsion unit is the propeller. The propeller is nothing but an energy conversion device. It converts the rotation of the motor into useful mechanical thrust to fly. Now, the propeller has two main specifications. First one is the length. Length is the distance from edge to edge. And the second one is pitch. Pitch is nothing but if we rotate the propeller a full 360 degrees on a soft solid medium, then the linear distance our propeller travels inside, that distance is called a pitch. Suppose a propeller is rotated 360 degrees in a soft solid medium and it travels 4.5 inches forward. That 4.5 inches is the pitch of the propeller. Then the navigation part of the drone has two main components. One is the GPS unit. The GPS unit shows us the location of the drone over the map. Same time, it helps us to get back the drone in case of any emergency or failure. And the second one is one electronic compass. The compass measures the heading of the drone, that is angle with the Earth's magnetic north. Then comes the inertia management part of the drone. Now, the inertia management part has two sensors called one accelerometer and one gyroscope. The accelerometer measures the speed of the drone at X, Y, Z, three different axes, and the gyro measures the angle or the tilt angle of the drone at X, Y, Z in three different axes. Also, there is a barometer inside which measures the pressure of the air. By measuring the pressure of the air, it defines the altitude, and the data comes from all three sensors sent to the microcontroller unit of the drone. Then the microcontroller unit performs necessary decision to control the flight. All four components are placed inside one electronic chip that is called flight controller, which is the brain of the drone. Then the fifth part comes the command and control. Now, the command and control part of a UAV has two different components. The first one is the radio or RC component. The second one is telemetry or the data link. Now, the RC communication gives us a 2.4 gigahertz radio frequency based communication between the drone and our remote. It has multiple channels to control the roll, pitch, yaw, throttle, and other parameters of the drone. Basically, we fly the drone with the help of the RC. Then the second one is telemetry or data link. The telemetry gives us a two-way communication between our ground control station and the drone. So whenever this two-way communication is established, we are able to see the battery voltage, the distance, altitude, flight speed, and many other critical flight parameters during the flight when the drone is far away from us. Also, with the help of this two-way communication, we are able to upload the autonomous flight mission, which we plan before data acquisition or spraying. Once the mission is uploaded, then drone will perform the autonomous flight. Now, this is a practical example of the components inside a drone. This is a 10-liter spraying drone. You can see the inside view here. The left-hand side image shows us there is a flight controller which comes on the inertia management part. Also, there is a power module which supplies power to the flight controller and all critical components. Also, there is in the navigation part, there is a GPS with built-in internal compass, and in the downward right side image, there is the GCS or ground control station, which helps us to control the drone with the help of telemetry and RC. There are many accessories like one obstacle avoidance radar, one terrain following radar, same time one pump. All these things operate on 12 volt, but the drone operates on 50 volt. So due to this voltage difference, many converters are introduced which converts the battery voltage into different level. Now this is an overview of what happens when we switch on a drone. First, the power goes to our power distribution board. Then all our speed controllers gets warm up and we hear a noise from the electromagnet of the motor. At the same time, the flight controller gets power, all our accessories gets powered on. The GPS unit starts for searching satellites and our IMU starts warming up. Then whenever we arm the drone, our motor starts, and when we push the throttle over 50, our drone takes off. Then here you can see a critical parameter for any drone, which is called thrust to weight ratio. The thrust to weight ratio is calculated by dividing the total maximum thrust of the propulsion system with respect to aircraft's weight. So that means if our four motors generating 4 kg thrust, the weight of the drone is 2 kg. So 4 divided by 2 is around 2. That means we have a thrust to weight ratio of 2. So thank you.
After this, we should break for lunch. We must be hungry.
Yeah, so I'll
Lunch make presentation.
Okay.
We can break for lunch and come back.
Yeah. Should.
Live demonstration will take time.
So they can move like
You can have your friend.
Pratik.
So you can move the drone if you want to the site.
To the side, no? Or do you have to this?
Yeah, yeah.
But you correct.
Correct. PPT. Okay. So good afternoon, everyone. My name is Purushothaman from a company called Electrotech Chennai. So before I start, I would like to thank Dr. Sabu and his team, Director Sir, and the CIFRI team for giving us this opportunity. So the basic goal of a hyperspectral remote sensing UAV is you have to fly, collect the data, process the data, and then get a solution out of this. So that is a basic objective. Yeah. So there are three components involved in this. One is the drone, which my engineer Pradeep, he has explained it very neatly about the drone, what type of drones we have, what is such, how it works, everything. My part is about the sensor. That is what I'm going to cover. And data processing part and data handling, Dr. Rajiv sir and Amrita ma'am is going to cover this. So my topic is sensor. So we all know about hyperspectral remote sensing. What is the advantage of this? What is the power of the hyperspectral remote sensing? So with the hyperspectral remote sensing, you can do anything. You can detect, you can classify, you can discriminate, you can identify, characterize, and you can quantify also. So that is the power of your hyperspectral remote sensing. So we cover the region 400 nanometer to 2500 nanometer, but one single camera, one single imager will not cover this complete range. So we have different types of cameras available, and it all depends upon the detectors we use. Up to 1000 nanometer, we use a silicon detector, and from 1000 to about 1000 nanometer, either we use InGaAs detector, Indium Gallium Arsenide detector, or MCT detector, mercury cadmium telluride detectors. So the sensor, what right now we are having is the nano hyperspec imager, which is something like less than 600 grams, the total weight of the camera, which has a built-in memory, which is a 480 GB solid state drive, so that you can save the data when it flies. So you don't need to have a separate computer or something. And also it has a built-in GPS. So we don't use the GPS unit of the drone. We use our own GPS integrated to this hyperspectral imager. So it covers the spectral region 400 to 1000 nanometer. We call it as a nano hyperspec VNIR, and it has 270 spectral bands. It means 1000 minus 400 divided by 2.2 nanometer will give you the spectral bands. So every 2.2 nanometer, you are going to have the data. 400, 402.4, 2.2, 404.4 like this. So that is why we call this as a hyperspectral imaging system. And we are going to have a spatial band of 640. So 640 is our spatial band. So there are two technologies currently available in the world for hyperspectral remote sensing for this one. One is called the framing technique, and another is called the push-broom technique. So the framing techniques, we have different types of hyperspectral images: liquid crystal tunable filter imager, acoustic optical tunable filters, FT images, compressive images. The push-broom images, there are two types. One is the transmission type and reflective type. Our head-wall hyperspectral images are all our reflective type imager. The difference between these two is very simple. Framing technique is your X and Y are the spatial dimensions, and over a period of time, you are going to change the wavelength. It is similar like your mobile phone camera or your RGB camera. You're going to take a scene with a click, and then you're going to put another filter of 405 nanometer, click, then 410, click, like this. So your Z is going to vary. Your wavelength is going to vary over a period of time. Whereas the push-broom, your x-axis is a spatial, and also your wavelength is spatial. So where we are going to take the y spatial over a period of time. So we are going to stay on the first line. We are going to capture the full spectral region 400 to 1000 in one go, and then we are going to move to the next line. So that is why we call it as either it is a push-broom imager or line scanner. So what is the advantage of this? The framing technique, you know that it is not good for moving targets. So we cannot use it for drones, or we cannot use it for anything which is moving. So it also have a wavelength limitation. So you cannot use it for a wide, big range, 400 to 1000. So it is very, very like a multispectral camera or something like this. Whereas the push-broom technique, that is one of the preferred technique. You can use it in the drone so that you can capture line by line while flying. And there is no limits for a spectral region. The framing techniques, as I said, there are tunable filters, compressed images, which are all very costly, and also it is very large and expensive to handle. So it is having a lot of disadvantages of this, and also some of them are mature technology. So it is outdated technology, so it is not required. Whereas the push-broom images gives you exact co-registration of pixels, and it is having much higher SNR, so that it is meant for airborne applications. So push-broom images is one of the preferred technique used by all the space agencies like ISRO, NASA, JAXA, everybody. In the push-broom, as I said, there are transmissive type imager and reflective type imager. The transmissive type imager is the layout is like this. So where it has something like 9 to 18 optical components. So the light passes through the optical components. So you know that when the light passes through the optical components, either it will bend or it will refract or it will do distortions. So finally, the image is not good one when you use this transmissive type imager. So it is low cost, but you will not get a crisp image. Whereas the reflective concentric imager has only one optical component, we call it as a concave mirror, just one optical component. So the light which is coming from the target, it passes through the slit. We have a small narrow slit, so that passes through the slit and it falls on the concave mirror, and then it is reflected to a grating. So you know that grating disperses the light to very fine nanometer. So 400 to 1000, it disperses the light every 2 nanometer, and it falls on the another concave mirror, and then it goes to the detector. So it looks very simple. It is called concentric imager layout. So this is how the imager looks like. If you open the nano imager, this is how it looks like. So we have a 4 optic lens. So the light enters through the lens, and we have a narrow slit. So the light passes here to the spectrograph, and then it falls on the grating. The grating disperses the light, and it falls on the detector. So it is just one pixel. Suppose we have a range of pixels, 640 spatial pixels. So we are going to have the complete swath. We are going to take the image. So this is one of the preferred technique. And because of this reflective concentric technique, there is no distortion in your image. So you don't need to do anything about keystone distortion or smile distortions, something. Your image will not look like this. So it will be like a very square pixel, you will get it. And also, since there is no stray light problem, your image looks very clear, crisp. If you have a stray light problem, then it becomes very dull. It looks very this one. So imagine that you have a scene like this. So normally when you take a RGB camera, you just go there, you click it. So you get the complete scene. And each and every pixel of your scene is about your resolution of your camera. Whereas in our hyperspectral camera, we introduce a narrow slit, a very, very narrow slit. So it is going to see only a portion of your scene. So what happens is you have to move, you have to fly like this. One by one, it is going to capture. So that is why push-broom images are also called as line scanners, line scanning images. So this is how it is going to capture the whole scene. So we have captured this every slit-wise we have captured. So now you imagine that you have a hyperspectral image of this. So the first slit, the first spatial pixel falls here, and you are going to get a 400 to 1000 nanometer. Then similarly, you are going to get from all the pixels, and then finally you are going to get a spectral cube. So that is what we call it as a spectral cube. So for the complete scene, you are going to get for each and every pixel 400 to 1000 nanometer. So that is how the push-broom technology works. So basic system configuration is you need to have an imager, you need to have a hyperspectral camera, and a correct data acquisition system and a platform. Since it is a push-broom technique, either you have to move the camera or you have to move the scene. So for moving the camera, we have drone, we have outdoor units. Whereas in the lab, we have a translation stage, like a conveyor belt, where we move the sample, your camera is fixed. So typically customers start with lab applications. So that's how we started our relationship with the ICAR. So first we started with the non-imaging spectrometer. We have lab systems. We developed a lot of applications, and then we started going for outdoor, and then we are flying now. So it is not that straight away we are flying. So we started with the basics. So this is a basic lab application system where we have a camera. Either we can have 2 cameras at a time, VNIR, and also we can have a NIR camera. We can also have a sphere camera. And these 2 are light sources that is going to illuminate the sample here. And this is the translation stage where it is going to move X, Y, like a conveyor belt. So it is going to illuminate the sample, and this is going to capture the data, and you are going to get the hyperspectral image of your sample. So based on this, we have different configurations available. So in a lab, typically you take a sample, you scan it, you get the hyperspectral data, you classify the image, and then you process the image, you develop some regression model, and you're going to get output, research. And at the same time, you can give the same reference samples to your lab, and you can get the lab results, and which you can use it for building the models, and then you're going to get the result. So this is how you are going to develop the models, classify the images, everything. So that is why it is called as R&D lab setup. So one of the example we are very successful is the histamine detection in fish. So where we take the samples, fish samples, we capture the image of this sample with the VNR camera with a light source illuminated. So we keep the fish sample on the conveyor belt. So we move the sample and we capture the image, and within a matter of few minutes, you will be able to map the histamine contaminations in your fish. So this is one of the successful application where we are doing it. So we have different types of scanning stages depending upon your width of the sample and the type of sample. And also you can take this camera outdoor with a rotation stage. We call this as a rotation stage, where you can mount it on a tripod rotation stage, and you can rotate the camera. You can rotate 360 degrees, and you can capture the scene in front of you for outdoor applications. You can also use a VNR camera. You can also use a sphere camera. So anything you can use it in the field. When it comes to the airborne applications, as I said, you have a package here, which is completely of drone, hyperspectral imager, everything. The most important part is the field of view lens. So what is the lens you have to choose when you are going for outdoor application? What is the lens you have to choose for indoor applications? Before we go that, you should know these terminologies. Spectral resolutions, we know that it is number of nanometer captured by each pixel. In our case, it is something like every 2.2 nanometer we are capturing. So 6 nanometer is our spectral resolution. The field of view is nothing but the width, swath. And the instantaneous field of view is the pixel size. That is 1 pixel. What is the size of the pixel? So this is determined by your lens. What is the type of lens we use? So we call it as a field of view, angular field of view. If it is 25-degree field of view, we should calculate what is the swath and what is the pixel size. So for example, if you have a 4.8 mm lens, which when you're going to fly at a 20-meter altitude, you are going to cover a 19.73 meter width, that is swath. 19.73 divided by 640 spatial bands will give you 30.83 mm. So it means like something like 3 centimeter, you are going to get the resolution, spatial resolution, if you are flying at 20 meter height. If you fly at 120, it is linear. So if you fly at 120, you're going to cover almost like 118 meter width, swath, and 185 mm. 18.5 centimeter is the pixel size. If you change the lens, then accordingly your width and the spatial resolution changes. So you have to choose a proper lens, type of lens, depending upon your swath and depending upon your spatial resolution you require. We supply accessories which is required for airborne applications, like a known calibration torque. Because in your scene, when you capture a scene, in your scene you should have a reference pixel. So based on the reference pixel, you are going to calculate the reflectance, you are going to normalize it, you are going to do classifications. So we supply a torque which is of 3 meter by 3 meter, and it's having 3 different reflectance levels, 56, 33, and 11% reflectance. So we keep this as a reference and we normalize the other pixels in the scene and we calculate the reflectance values. So we supply a complete software package. The first one is the flight planning software, which Rajit knows this, Pratim knows this, where we first plan the flight like this. For example, we want to fly like this. It is autonomous mode of flying, but we don't capture the complete data. When you take off and landing, we don't want the data. It is a junk. So we draw a polygon, a region of interest like this. So we do the flight planning. We also create a polygon. 2 things we do in the flight planning software. And this flight plan is loaded to a drone. This polygon is loaded to my sensor. So when the flight starts and once it reaches the polygon, my sensor triggers and it captures the image. And once it leaves, it stops. So the flight plan goes here and take a turn and come back. Then the trigger starts. So it captures only the region of interest where I want to take the data. So that is the purpose of my flight planning software. And also we supply a sensor control software, which is called Hyperspec 3, which is to configure the sensor. Each sensor requires its own exposure time, frame period, all those things. So using that, we are going to configure the sensor before we fly. Once we fly and get the data, we are going to use the spectral view software, which is supplied along with the system processing for post-processing the data. So when we capture only the raw image. It is not reflectance, it is not radiance, it is nothing. It is a raw image, digital number versus wavelength. So then we convert this into radians, watts per radian per meter square per nanometer per pixel. Then we take the scene reference and then we convert this into reflectance so that you get a reflectance cube. So all these things are all done with the spectral view software. And we take line by line And then we do all these things for the complete line, and then we stitch it, we mosaic it, so that we get a complete image like this. So hyperspec 3, as I said, first you have to connect the GPS and make sure you are getting a lat long position of your position where you are going to fly. Then we put the white plate, and then we do the exposure time and frame period settings. And my exposure time and frame period depends upon your outdoor ambience lighting condition. If you have a very bright light, then my exposure time is very less and I can fly fast and collect the data. If it is cloudy, then I have to increase my exposure time so that I can integrate more light, but I need to fly slow. So it is a trade-off between your exposure time and framing period. Once I set the exposure time and framing period, I can calculate what speed I want to fly. At this speed only he has to fly. I have to inform my pilot to fly at this speed. So that is the purpose of the hyperspec 3 software. Then I'm loading the polygon. Then I loaded the polygon where I'm going to take the data, and then I start the capturing. So we take the dark current, we close it, the camera with a black cap, and we take zero current. No light, nothing. So it's a dark cube. Then we open and we fly. And then after landing, we are going to stop the capture, and that is what the raw cube is. So that is what the purpose of your hyperspec 3 software. So once you are done with this flight, so this is a small video at IRI for first flight. So first we take off manually, and then we do the GPS initialization. That is what after lunch you are going to see that. Then it enter into the automatic mode, autonomous mission. Then it completes the mission, and then it comes and stops. Then we take a manual control and we land it. Then after landing, we are going to stop the acquisition and we are going to transfer the file to our computer if the battery power permits you. Otherwise, you can come to the lab and you can transfer it. So once I have the data, then I'm going to start the processing. So data processing technique is totally a complex one, which requires a lot of experience and a lot of techniques you need to know how to do this processing, which I think Dr. Rajit and Amrita ma'am they're going to do this. So we take the raw spectral data, we convert this into radiance, we convert this into reflectance. We take the GPS data, and then if you have a LiDAR, then you can take the LiDAR data, or you have to take the DEM, local SRTM, DEM file, and then you are going to do the ortho rectification. So you know that you are flying in a drone, so it is not a stable like your manned aircraft. So it is going to have all type of raw pitch problems. So the raw image looks very ugly. So we have to do the ortho rectification to make the pixel square. Then we mosaic it because it is a line scanner. So line by line it is captures. So we have to stitch all the line to get a complete image. So that is the purpose of the software spectral view. Once we have this data, then you can go for classification, modeling, and all those things. So we have a lot of customers. IRI is our major customer. They have 400 to 1,000, which Dr. Sahu was telling it was 65 lakhs at the time. Now it has become 85 lakhs or more. And we have a 400 to 2,500 nanometer. We have supplied it a couple of years before. It was costing you 4 crores or double. For airborne applications. If your application is only for lab, then it costs you only 50 lakhs, 70 lakhs. Because airborne requires a complete package, software, everything. So we have IIT Bombay, Space Application Center, Ahmedabad, Trivandrum, NMDC Hyderabad like this. So this is Dr. Sahu and his team. So first installation. So also there are plenty of YouTube files available, and also in Edwall website you can see a lot of webinars, a lot of details available about the application, about the products, everything. And this is my first flight at IRI. I don't remember, it's a top field, I think. So where we went there and we took the first date. So it came very good with respect to that image. We keep some known targets before we fly, so that once you do the ortho rectification mosaicing, you should get the same image. If I have a 3 meter by 3 meter a painting, the final output should have same 3 meter by 3 meter. That means your pixels are square. You have done a proper post processing. So that's how we keep a lot of known reference samples, and then we do the processing. Thank you so much. Thank you.
Engineer Purushottam and Engineer Pratim Chatterjee for your nice presentation and important presentation on drone technology, basics of drone technology and spectral imaging. Now we are running late according to our program schedule. Now we break for lunch, and it is arranged at Bhagwati Guest House. After that, the live drone demonstration will be there. in our field ground, just behind our anesthetic building. And after that, the next session will be started. So we'll go for lunch. Thank you.
So I blocked everything. Go for lunch. First, you have lunch. Okay. Online bata do उनको chat online chat
So for online participants, we'll start our next session.
practically in the live.
Practical in the live demonstration will be doing practical. And after that, second session will be started after
No,
3
it will
o'clock.
start at 2 o'clock. No? अभी क्या time है?
Abhi 1:30. 1:40.
So can we do at 2:20? Start.
Live demonstration.
Live demonstration.
So we'll start.
We'll have live Zoom
We'll have live Zoom for live drone demonstrations,
followed by class.
followed by next session classes, no lectures.
that much more longer time, so that you get a sufficient light inside. So the exposure time is very critical. There is in the software, there is a provision to see the exposure time and the signal level. Your signal must not get saturation. After having 20 minutes and if the pixels are saturated, then your rectifier is not up to use. So before we fly, we do the configuration. We adjust the exposure time and then we calculate the frame period. So we know the exposure time. Now, what time, how much time I have to collect the data? Either equal or more than. So if I can, then my frame period must be 1 or more than that. I know. So I have to tell my pilot, you have to fly at this. So accordingly, you will plan this flight plan.
Sound mute.
Then next is
sound is
how much area you want to cover and what is your pixel size. So accordingly, I have to determine my altitude. So generally, we more than 50. So that is what once it is done, something is configured, then I have to inform my pilot to make the final checks for flight. So then he will load the flight plan to his drone, so that accordingly it will fly. I will load my polygon to my sensor so that it captures only at the region of interest. While takeoff, calibration, all those things it won't take. Once it goes to my region of interest, it captures. So that I have to enter. Once it is done, we are ready to fly. So once they start to take off, we always take off and land manually. We don't automatically. So we take off to a safe altitude, for example, 20, 30. Then we calibrate the sensor of the drone. So drone has magnetometers, drone has accelerometer, and my GPS is also having accelerometer. So I have to calibrate this. So after takeoff, they rotate the drone clockwise 3 times, anti-clockwise 3 times. So that my calibration is done. Magnetometer calibration is done. Then they fly opposite your side. 100 meters, very fast they will fly. They will take a turn and come. So that will calibrate my accelerometer. Once it is done, he will enter into auto mode. Then it goes as per the flight planning. It goes and it finishes the last line and it stops. It will be hovering. Then we take a manual control and then we land it. After landing, again we connect it to the laptop. We stop the capture. Then we go to the lab and download the data. Maybe first 1 or 2 frames we just download and see whether it has captured or not, just to make sure. That's it. So flight planning is very important in this case. So you have to maintain the speed, you have to maintain the altitude. So these are all DJI drones, which is much better. Whereas the Indian drones, so we need to be very careful. So we have RTK enabled drone so that it has to maintain the speed. So it should not fly like this. It has to fly smoothly. And similarly, pixel size will vary. So all these corrections have to be taken. Yeah. So now the gimbal is oriented such that my camera looks down, not it. Because while flying, it has to be there. While calibration, we keep it like this. The camera, we calibrate the camera, and just before takeoff, we put it like this and fly. Similarly, while landing, we tilt the camera like this, and then we land. So we don't land like this. Otherwise, just stones will hit your camera. So we just make it and then land. The recent hyperspectral images doesn't require a gimbal. So we have a very high performance GPS, which is of centimeter level accuracy. So that you don't need to have a gimbal at all nowadays.
So before you fly, you have to go to the site and you have to have a look around the site. What is the tallest structure available? Whether the surface is flat, something like this. Where you have to take off and land. Same thing you have to select. And your takeoff point must be less than 30 meters from your waypoint, first waypoint. So I cannot take off and start my mission outside the gate. So it has to be somewhere very close to this. So those are all the things in the flight planning we will do. Any question before you take off? Any question? Anybody have? So he's making it ready where the phone is, making it going to update it so that if something goes wrong, then it can come back to the home point. And mission planning is done. This way it will back. But before that, as he says, optimization is most important. Because of the time constraint, we are not going to do all those systematic approach what is required usually to. So we collect a dark current means the camera. We put a lens cap over there and close it so that any noise, even if any radiations, if any noise that is recorded, and we take with that, we collect the maximum radiations what you can. So that is what the minimum and maximum data what you can receive. Once that is taken, then we do all processing in the processing software on the raw data to reflect us. That's what we do. And that's a bigger one is already has told you about the state which goes for optimization in the field conditions. So once it is done, then we go for the planning and data capture. Now, though we have done everything mission the automatic mode, but we will flying manually because of there is a jam area close by can. So we are not doing automatic mode mostly. But as he says, we'll take up to the height of 30 meters. Then we'll hover around to make it calibrated. Then put on the automatic. Is that ready? Now I'm going for scan line, to line data acquisition. Right. Yeah. So now it is coming back for landing. It has taken a turn and coming to home point. Did it? So once it reaches the home point,
it has a retractable landing gear. So right now they are on retract position. Now I will deploy the landing gear.
Next. Connecting the cable. Yeah, so after landing, you don't need to switch off the payload power because your entire data will get corrupted. So we have to connect again the Ethernet cable to my payload, to my camera, and I have to stop the capture because before I started the capture. So I have to stop it. Once I stop it, I will know whether the data is saved or not. I can go to the folder and see what is that, whether the data is saved or not. It will be in gigabytes. If you fly for a 20 minutes flight, you will be having something like 30 gigabyte raw data. Then you convert this into radians, it becomes 60. Then when you convert it into radian reflectance, it becomes 120. So something like the final data will looks like 4 times than your raw data. So you need to have a very high supercomputer to process this data. Just a 20 minutes flight data actually. So that's how we do the flight planning and we capture the data. So data capturing looks very simple, but it needs a lot of work behind this. So once you have done, you have successfully completed the mission. Thank you. So it's not easy as it is explained. For a 5 minutes flight, many times we take whole day. Yeah. Still, it's not possible. Many times light goes up and down. Now you see there is no light. It's gone. Many times the camera doesn't work. Many times cable doesn't work. Many things goes wrong. So one has to get prepared and always you go that mission is going to be not possible today. So sometimes the battery endurance time is only 30 minutes. So by the time you calibrate everything, then hardly 15-20 minutes flying time will be. Again, you have to change the battery or you have to take the battery to nearest place to charge it. These are all practical challenges, problems what we have. So we have a 3 set of battery for that purpose. We have 2 drones for that purpose. So that we do everything at lab, bring to the field so that within no time we finish it. And you know, this is a very conducive weather to enjoy outside. Peak summer in Delhi, 47, 50 degrees, nothing works. Sensor, laptop, nothing works. It's big challenge. Still, we try to work on that. So there are many, maybe when presentations, you will see the challenges, how complex it is. And the data, what you capture, as I said today, 5-acre field is almost 40 GB data we capture. So it is not a MB, it is GBs. So each time you process, little processing you do, again, 40 GB hard on. So within no time, 8 TB hard disk goes up. So, and you need to kind of a supercomputing system to particularly this kind of data what you have. This is again up to only 270 channels we have, 270 bands. Each pixel you click, you get 270 data points. So pixel means whatever the area you're looking at. And the other camera, again, that is 600 channels. Is again a huge data. It's a bigger one. So after this, I think this is what you could see the imaging drone. So we have multispectral, hyperspectral, RGB. You can integrate fly. At a go, we fly everything together. On these 3 cameras integrating together, we fly. So at a go, you get a multispectral, you get thermal and also hyperspectral. Then you have RGB also. So you have 4 sensors capturing data for analysis. Our purpose is once you do analysis, then same variable map should go to the drone, spraying drone, and go for the spraying wherever it is required. That's what the work we are doing now. I think the team from CIFRI, they will be demonstrating the spraying drones. Kaushik and his team is going to. So there is a water with a 10-liter tank. They are going to show you the spraying drone. Kaushik, can you go ahead? Are you ready? Yeah. So it is statement challenge.
Sprayer.
your master switch on. I am in progress. That healthy.
এই এটা প্লাই করবে
ওড়াচ্ছে ড্রোন।
ওদেরকে বলবে আমাদের ফ্লাইটটাকে ফেরত দিতে করতে
আচ্ছা
বলবে এইদিকে ফটোটা ওইদিকে
আচ্ছা আচ্ছা ঠিক আছে।
Chemicals, and for one role is here for broadcasting. That is for feed distributors. In culture facilities, we need some feed for feed. So in that case, we just using that feed and we evenly distribute over the water bodies. So now we are having chemical capacity. So we are trying to use and showing to the farmers that what are the benefits, potential of drone technology for feed management. So later on, it can be customized for means increasing the payload capacity so that it can be go for some large water body and go for some heat distributions and different chemical spraying or insecticides. And so this is the zone having chemical. It has three configurations. One for sprayer, and it can be go for means we have to change some configurations for feed distribution. So we have to load the to some solid feed and we can distribute. And another is the attachment is the sensing. Imagine also we can do. So three configuration is there. So it is costing around 13 lakhs. Okay. So initially it is high in cost. So if more standardized those ones, so it can be subsidized in later on.
Foreign sector FPO this can be brought. Government will take a subsidized here. FPO will in a central or KVK it will be placed and you can have a hiring system. If anybody took a hire, you will deposit certain money. Then you can have revolving scheme like that. You can utilize for the repairing other place. This is a larger, this initially tractor. So similarly, drone is coming for harvesting. So everything is step-wise evolutions. So you can utilize maybe a KVK for fish purpose, or maybe agriculture purpose, or any horticulture purpose. So multiple use you can do something. As spare, then suppose same you have a one drone. Next day you can configure just like Madam told. You can change there is a feed dispenser you can use. Next day you can use for feed purpose. Or if you want sometimes granules fertilizer application also, you like feed applications, you can go for fertilizer applications. Like potassium permanent distinct. If you dilute it, it has some problem. It will block the system. Therefore, we are telling full grain you can apply, just like a feed. So it will fall in the water, so it will be the disposal. So these type of things, it can be multiple use that can be. Only that we should have a pilot. Means like people are talking like a drone DP or youth you can train because 50,000 for a pilot training. Then we can. Then you can try to the
So what is only what is it? We know. Yes. Thank you so much. Yeah, everything is fine. Yeah. Thank you. Sure, sure.
So good afternoon. I think drone flying made you a little lighter, having very heavy, tasty lunch. So now we'll go for data processing, something related to the sensor, pre-processing, then data processing, followed by drone spraying. And now it's 3:10. We should finish by 5:30 these three presentations, followed by interaction or discussions, then concluding. So to start with, I am inviting Dr. Amrita. She's going to talk about sensors and sensing from drone, principles and steps for image acquisition. Dr. Amrita, Dr. Rajit, Dr. Tarun. Tarun couldn't come because of bad health. And both doctors are the research associates under this NEPA program. And Dr. Amrita is a PhD in computer science from Delhi Technological University. She works on big data analytics, AI, Gen AI, and all hyperspectral remote sensing is her expert. And Dr. Rajit also expertise in hyperspectral remote sensing, more on geological mapping. So both of them are my strength with respect to NEPA program and all research activities what we do. So there's going to be relay presentations. Now I would request Amrita to start with.
Very good afternoon to all of you. I am Amrita and I take this opportunity to explain to you some of the basics and the process of data acquisition. So after this live demonstration, the process has become a little easier for me to explain to everybody because now you have seen the imaging sensor as well as you have seen the spraying drone. So now it will be comparatively easier for you people to understand what I want to tell you in another next 20-25 minutes. Uh, I would request the admin, can you please take up that upper portion? It is actually hiding the slides.
That actually automatically opened.
So you can minimize it or take it towards the side. Yeah, thank you so much. So the title of my today's presentation is Sensors and Sensing from Drone. I, along with my dear colleagues, Dr. Rajit, Tarun, and Pratin, we would be taking you through the next three presentations of today's part. So the first slide that I want to explain to you, which has been shown by Dr. Sahu. So here I would like to tell you and bring to your focus the different types of sensors that are available for remote sensing. We can take the data from the ground by using various ground spectroradiometers like ASD field spec, which Engineer Purushothaman sir was also explaining to you in his presentation. We also have different types of UAV sensors. One such sensor you have already seen in the live demonstration, which is the hyperspectral nanosensor that captures the data from 400 to 1000 nanometer spectral range. On its right side, you can see another hyperspectral sensor, which is co-aligned, head wall co-aligned hyperspectral sensor that captures the data from 400 to 2500 nanometers range. On the extreme left, you can see the thermal sensor. And on the bottom, there are two sensors, which are multispectral sensors that are available with us at ICAR, and one is LiDAR sensor. So these are all the sensors that you can mount on any UAV or drone. Then you can also mount these sensors over aircraft like Everest, in the Everest NG JPL, NASA had put across one sensor. There is also another sensor which is called HiMap sensor, which was also it was developed by an Australian company and it was put over an airborne mission. We have also many types of satellite sensors, the sensors that can be put that are put with the satellites, and we are regularly taking the data from these sensors like Sentinel-2, Prisma. So you can see from ground to satellites, there are n number of sensors that are available at our disposal. We can take the advantage of these sensors for remote sensing applications. The role of each sensor, definitely for a particular application, you might be taking advantage of ground spectral radiometers or
For your application, you might be using the sensors on board the UAVs, or you can take the advantage of satellite sensors. But there are certain pros and cons or limitations and advantages in each case. Like if I talk about ground-based sensors, we can only get the point data. The area coverage is very less. These are very resource intensive. That means a lot of cost, a lot of resources are involved when we need to take the in situ data collection. But the advantages are the data that you get is very accurate, it is reliable, and it is also the primary data that you can use for validations and for many other purposes. When we talk about UAV-borne sensors, there are many limitations. That is, you can get only the local coverage. It is weather dependent. Whenever you are going for a UAV-borne mission, you need to take care of the environmental conditions, whether they are in favor or not for that data acquisition campaign. Regional restrictions are also there. However, the advantages are you get real-time images, because when we talk about sensor data, data from the satellites, generally that data is dependent on the revisit time of the satellite. So suppose you want to capture the data, say today or tomorrow, maybe the satellite is not oriented towards that place and you might not get the data. So in that case, you for real-time imaging and for on-demand imaging, you can take the advantage of UAV-borne sensors. You can get very high resolution data, and it is also very helpful in achieving the objectives of precision agriculture. When we talk about sensors on board the different satellites, limitations are spatial resolution. The resolution is very coarse, but with the UAVs you can get very fine resolution data. Cloud cover is another issue. Suppose you have got the data, but during the time the data was being captured from the satellite, if there is high cloud cover, that data is of no use to us. And temporal resolution is another issue. That means you cannot take frequently the data. It depends on whether that satellite is oriented towards that place the next time it is coming. So you have to be dependent on the revisit time of the satellite. But the advantages surely here are you get a very good global coverage, reliability, and it is very cost effective. That means in many cases, many satellites are providing free data. So you don't have to spend even a penny to get that data. So you can see that this is a very scalable kind of approach. Right from ground to satellite, you have a lot of sensors available with you. Depending upon your application, you can use the data available from these platforms. On the right-hand side, you can see there are different sensors on board the drones. You can see the nano hyperspectral sensor which you just saw in the live demonstration, and also you can see the co-aligned on the extreme right side. This is the hyperspectral sensor that captures the data from 400 to 2500 nanometers. Down below, you can see on the left side, there is a spectra that has been obtained from RGV and multispectral vegetation. This is a multispectral vegetation spectra. And on the right, you can see the spectra that has been obtained, the hyperspectral data that has been obtained from varied sensors, that is ground sensor, and also from nano and co-aligned hyperspectral sensor, and also the sensor that is on board the satellite. So this is how you can get the spectra from different sensors on board different platforms. Now I would be taking you through the entire process of drone data acquisition to the analysis. You have seen in the field that how we actually you did not see the integration of the sensors in the drone. You had already seen the sensor that was mounted there on the drone itself. So the first step when we go for data acquisition is basically defining the site and its ambient conditions. So we need to be very sure about the area, about the location, area of interest, where we want to capture the data and what are the ambient conditions there. The second step comes as the integration of the sensors with the drones, followed by mission planning. That is, we need to plan the entire mission, the entire course of the drone that it will follow during the data acquisition process. Then we set up the flight parameters, that is what will be the height, what will be the speed of the drone at which it will capture the data, followed by calibration, uploading the mission to the drone, image acquisition, wherein we are actually acquiring the image in the field. Once the data is acquired, we transfer that, we bring the drone back to the home position, we transfer the data, and then we go for image preprocessing and analysis, through which we get the resultant imagery. So on the left side, you can see this is the mission planning, how we do on the softwares that are available. So during the mission planning, we set up the flight parameters like the flight speed, the altitude, the overlapping side, that is how much is the side overlap during that flight. Either generally we keep 40% for hyperspectral, but for multispectral it is around 70%. So side and forward, both we see the overlap. Then what is going to be the UAV speed, etc. These are all the parameters that we set during the mission planning. Then we generate the flight route and the polygon, that is, we define that area. We generate the route that the drone, the UAV will be following in its course, and the polygon within which it will capture the data. The second part is sensor integration. Here you can see there are two sensors integrated. One is hyperspectral nano and the second one is hyperspectral co-aligned. So the first step is we get the imager ready for the capture. We set the exposure and the frame period. So these are all different parameters we have to integrate, and we have to set the polygon that we have defined in the mission planning that we have to integrate. Then we collect the dark reference data. We enable the GPS trigger, and then we go ahead with the data. The second part is sensor calibration. In sensor calibration, first of all, we go for the live feed, wherein we see the data that is coming. Then we do we set the exposure, we set the frame period. These are certain parameters that we have to tune in during that part. And then we go for the data. We upload the polygon into this into the software that we are using for that particular sensor. After uploading the polygon, we go for the data capture. The next step, this is already you have seen, we had put a 3 by 3 meter tarp on the field. This is that panel that has been shown here. This is reference tarp for radiometric corrections. Then we go for drone monitoring. Then the drone goes into the field for data acquisition. And then we go ahead with the data transfer. And this is how we get the raw scan line. So today in the field, you saw that the drone had covered 2 scan lines. Once we transfer that data, this is how we get it in the system. So once we have got these scan lines, we can do the pre-processing of these scan lines, and we get the pre-processing processed image, where we do the auto rectification and the mosaicing, which is carried out using DEM and sensors metadata. And we also take into consideration the yaw pitch and altitude corrections are also done in this step. Then we go with the spectral smoothing and masking, followed by whatever end members we need to extract. The spectra that we need for a purpose, followed by computation of vegetation indices, modeling, and the prediction mapping that we do for our application purpose. So this particular step that sir was telling, that it is not just that we take the drone to the field and we fly and start acquiring the data. We need a lot of things, a lot of pre-planning is required before the mission, and there are many necessary equipments are required for drone mission. These are some of those which are shown here in this slide. We need to do necessary preparations before a mission. That is, we need to have a clear mission objective, that what data, in which conditions, what we want to capture. We need to be very careful of the airspace restrictions, like sir told in the field also, that we could not fly because there is a cantonment area nearby, so we could not fly in the autonomous mode. That is why we had to take the flight in the manual. Similarly, there are many red zone areas where the drone flying is not allowed, and if you need to fly, we need permissions from the authorities for flying in that particular area. And in some places, there are restrictions of flying above 60 kilometers of height, 60 meters height, sorry. So we need to be very careful of all these restrictions before just going into the field and flying. That area should be free from restrictions, and we need to have the accurate details of the study area. We need to have the latitude, longitude values. The necessary equipments for the missions are, we need to have a calibrated drone. We need to have the charged batteries. So before going, we generally have a pre-flight checklist wherein we check whether all these things have been done, carefully checked or not before just going into the field. So the batteries should be charged so as to avoid unnecessary wastage of your time. Necessary tools for mission planning with full charge are required, and also you should be very careful of taking the sensors. Then we should have the softwares ready for use. Some of the softwares mentioned here are UGCS, Fixed 4D Capture, Mission Planner, etc. These are the pre-mission checks. There should not be no rainy conditions. There should be proper illumination conditions. We generally have certain time window when we are flying in Delhi. We do that data capture between 11 a.m. to 1 p.m. because that is generally the time when the sunlight is proper and adequate for the sensor to capture the data. The spin speed should be very low. The gust speed is also what we need to be very careful of. There should not be any obstacles at home point. Launch areas should be flat and hard. There should not be water area where we are flying the drone, taking off the drone from. Then we have to travel to the location with all the equipments. We go to the study area, we switch on the remote and launch the software. We do the data acquisition, unpack, switch off the drone, and we come back. So this is the sensor integration. These are different sensors. Today you have seen so we are also carrying the multispectral sensor, but I think we have not shown it to them. Okay. So right now you can see we have two sensors with us which we are carrying to Kolkata from Delhi. That is the Mika Sense, that multispectral sensor, and the nano sensor that you have already seen. This is the mission planning that we do. Herein we define the polygon, we define the corners where we have to take the data, we define the waypoints, then we define the home point from where the drone will take off. Then we define the path that the drone has to take. We define the height, we check what is the swath that is coming, what is the spatial resolution that is coming. There are different things that we need to be very careful of when we are doing the mission planning. And then the return to home point is also required to be kept while doing the mission planning. This is setting up the flight parameters that we have already discussed. That is, we define the altitude, we define the speed, etc. Next is the calibration. This you saw. I hope you recall and remember that when once the drone took off, it took 3 clockwise, 3 anti-clockwise rounds. Then it went straight and came back. So these are two types of calibrations that we do for the drone, which is IMU calibration and compass calibration. IMU is the inertial management unit calibration. This is basically done to ensure the accuracy and reliability of data. IMU provides data on orientation, velocity, position based on the accelerometers, gyroscope, and magnetometers, as Purushottam sir was explaining to you all in the field also. It is very important for accuracy of position and orientation, correction of sensor drift. It provides us with an improved GPS and navigation integration, and also it is very important to ensure that we have a precise flight control and stability. The next part is sensor calibration, which you have not seen in the field. What we do here is that we set certain parameters. We also collect the dark reference in this particular step, and then we go ahead with the data capture. So these two things we adjust in this stage, I would say, that is exposure and frame period, which is the time required to keep the aperture open for collecting the image. Bright sunlight requires very less exposure time, and exposure time determines the frame period. So depending on our exposure time, we will be knowing that what can be the frame period, and this frame period further determines the speed of the drone. Then we upload the mission into the polygon. The mission that we had created during the mission planning, that mission now needs to be uploaded to the drone, so that now the drone knows the sensor knows that this is the area, this is the polygon where the data is being captured. Then we go ahead with the image acquisition process. This is the data transfer process that we do once we are back into the lab. So we have in the field also, we generally check, it's a good practice that we check whether the data has been collected or not, depending on the number of frames we can see whether the data has come correctly or not. But the final validation and verification we do in the lab itself. So we click on the file transfer. First of all, we check whether sensor is connected or not. If the sensor is connected, you can see a red dot there. That red dot becomes green. So after the sensor is connected to the laptop, then we go ahead with the transfer of the data. After the data transfer, we go ahead with the pre-processing and the processing of that data. That would be discussed by Dr. Rajit in the following presentation. But for now, I would be giving you a basic introduction about two of the data processing softwares that have been developed in-house in IARI. There are many data processing platforms that you might have used or you might be knowing about, like NV, QGIS, ArcGIS, many different these sensor-based data processing platforms are available. But two processing platforms are there with us that we use for our purpose. One is HyperAgri, which is for hyperspectral data processing. This is the in-house software that has been developed for processing hyperspectral data captured on ground and drone platforms. It facilitates the calculation of spectral derivatives and spectral indices. We can compute over 120 hyperspectral indices in different aspects like nitrogen, chlorophyll, etc. It allows the resampling of hyperspectral data to multispectral data. This is another data processing platform which we call as DroneAgri, which is for the UAV image analysis of crop health. In this, there are two basic opportunities that are given to the user. One is for the field crop experiment, where you have the layout design with you, how the field has been set up. And the second is for the farmer's field, where the layout is generally not available. Then we go ahead with the vegetation indices calculation. We have almost 100 indices that are already there. So you might be knowing about NDVI, ARVI. There's so many indices that are available. So generally you compute the indices one by one. Here we have almost 100 indices available. So you can just immediately at the go, you can get the indices computation done for your multispectral image. We also have the options of modeling the thematic product, thematic map generation, visualizing the indices image. So there are many options that are available in this software, and it is very easy to use and handy too. This is a very small video that is of UAV hyperspectral data capturing. Can you play the video, please? Okay. So you have seen on the field, there were few steps that were missing on the field because of the sunlight. There was no proper sunlight, so we could not show you the calibration part. Play. Yes, play. No. So now you can see Pratim is preparing the drone and checking whether the drone is ready for the flight or not. This is a field at IARI. Dr. Tarun, he is not able to join with us today. So he is integrating the sensor with the drone. This is the nano hyperspectral sensor that you saw in the field today. This is connection of the GPS wires to the sensor. This I have already explained. So now you can see we are doing sensor calibration here for the mission. This is where we check the exposure and the frame period. We define those parameters. This is setting off the hyperspectral sensor to the nadir position. This is uploading of the mission. The mission that was planned previously is now being uploaded into the drone. Now, initially, it is always a manual takeoff that we do. You can see the mission, now the drone will go into that automation that it has been told to follow in this flight path. You can see that is the drone. So actually on the GCS, on your ground control station itself, you can see the position of the drone, how it is moving, where it is going. Now it has entered the polygon and it has started capturing the data. This is the first scan line that it is covering. Returning back. No, okay, it is taking the second scan line. No, I think it is coming back. No, it is coming back to its home position. And this is the manual landing. Then we go ahead with the data pre-processing that is going to be explained by Dr. Richard. This is auto rectification and the mosaicing that we do for the data and the analysis. Okay. So this is the life cycle of data analytics. This entire thing that I have told is summed up in this slide, wherein we go for the image collection. We also collect ground in situ data so that we can use it for the validation purpose. We go ahead with image pre-processing and processing, followed by analysis, wherein we do univariate modeling, multivariate modeling. We use networks, we take neural networks, ANN, feature extraction, different types of modeling techniques that are available. So these are all for the analysis purpose. Okay. So this is how drone data today. There is a big talk about big data analytics, why big data. So there are different V's that are of the big data, that is volume, velocity, veracity, variety, value, validity, vulnerability, vocabulary. These are all, so first of all, why we call these data as big data? Because you can see, sir explained in the live demonstration also that generally the data that we get is in GBs. You can see over there it is something around 36 GB data. So you do the processing, another 36 or 40 GB is added to it. So you can see how huge data, and this is what we are talking about, the nano hyperspectral sensor. If we talk about the co-aligned, the hyperspectral sensor that captures the data from 400 to 2500 nanometer range, the data goes up to 100 GB. So it is very difficult for us to process that data, and we need good computation powers. We even take the advantage of GPUs to process these data. That is why it is called as a big data problem. Then these are the different components corresponding to the big data, where we define the velocity, since it is captured at a good speed, generally around 3 meters per second. So these parameters, these add up to the complexity. There is different variety of data, the data that is captured under different conditions and every data has a different value. So when you need to analyze such huge volumes of data, you need to have your models, your algorithms need to be capable enough to support and calculate such humongous data. These two slides will be taking you through how we process for the multispectral water body image. So in case of water bodies especially, we face one problem when we are doing the multispectral data collection, is that when we go over to the places that is when the drone is looking at the water body, where there is no feature available, no ground data is available, no reference point is available, or there is no algae present, or phytoplankton is present. If that is a clear water body, it is very difficult for drone to register that image when we go ahead with the stacking. So that sometimes you might have seen in the data, the central part of the water body is generally missing. That is because we are not able to stitch that. During the stitching of the images, we are not able to register that particular part because of lack of the features available, the ground control points available. So these are the steps that are there for multispectral water body image, that is calibration. Then we go ahead with the feature extraction, stacking, followed by heading rotation, feature extraction, and orthomosaicing. These are some of the issues that are faced by when we are using multispectral sensor. These are the challenges, I would say, that the inbuilt GPS location monitoring of MicaSense is not accurate enough. So the applications like Pix4D and AGSoft, they use feature-based image stitching. In feature-based stitching of the mosaicing, common features or the edges are identified and later the images are warped according to the features for hyperstacking. Doing the same on water images where the water is clear without any features, it results into bad alignment and these images cannot be used for stitching. For this reason, the stitching clear water images is difficult until the water body is turbid or has noticeable features like algae, resulting in no data patches as shown in the figures below. So you can see the data of the water body where the turbidity is available or algae is available or any of a feature is available that helps us to stitch that image properly, we are able to do. But where there is clear water and no surrounding water body or present water body or the present feature inside that area, it is difficult and that data goes missing. Thank you very much from my side. Now, Dr. Rajit will be taking you ahead for the pre-processing and the processing of the data. Now you are clear with the data acquisition process, how we use that data, how we process it, that he is going to discuss in his slide.
Good afternoon to all. I'm Rajit and I'm taking on image pre-processing and analysis. So once we were back to the lab with the data, we'll copy the data and start the pre-processing. So this is the overall workflow of the pre-processing, where we are converting the raw spectral data to reflectance in the range of 0 to 1. So it's a step-by-step procedure. First, converting to radiance with the help of dark subtraction, then to reflectance with the help of white pixels collected from the star. Then we will do auto-rectification. So auto-rectification is just simply georeferencing, where we need the location information, the latitude, longitude, the Y data. So for that purpose, in the sensor itself, there will be a high-performance GPS will be there. So that GPS IMU data we can use. Along with that, we will use some DEM data also. If you are not having the DEM data or the LiDAR DEM data, we can also use the DEM from other third-party sites like SRTM DEM or Kato DEM. Also, we can use. But since we are working on UAV data having very high spatial resolution, it's always better to have a LiDAR DEM of the same spatial resolution. Then after auto rectification or georeferencing, then we will mosaic it. Mosaic means just simply stitching the frames to get a complete imagery of the field. And finally, you can see the complete imagery of our field in IRA canvas. So this is the conversion for a single imagery from DN to radiance and radiance to reflectance. But in most of the cases, we are working on a large set of data sets in the frames from 10,000 to 20,000 frames. So it's always better to do it in batch. So this pre-processing always will carry out with the help of the software provided by the sensor people. So this is the software provided by the headboard for spectral view for doing the pre-processing. So this is the batch software provided by the headboard. We can just give the input of the folder. So it will run all the files inside that folder and you will get the output. So the batch processing we can use for converting from DN to radiance and also radiance to reflectance. So before converting to reflectance, we will classify the pixels from the white arc, all the white pixels, the maximum reflectance will collect, and those values will be used for normalizing the values between 0 and 1. And here you can see this is a batch process running of around 34 raw data cubes. In a single stretch, it will run and we'll get the images. So we have the high performance GPS of the sensor where it will collect the path, the route of the drone. So this data is very important for doing auto rectification. But since the drone is not stable, it's always better to calibrate the IMU GPS file before starting the auto rectification. And this calibration we can carry it out using the base station data. So we are also using a base station. So base station will switch on and keep it on the field 20 minutes prior to the flight. So it will keep on loading the data. And after completing the mission, we will take the base station data also to just calibrate. So after calibration, you can see that pink lines, the pink lines indicate the path. This get calibrated. I don't know whether it's visible. Get calibrated and you can see a green line on the right side. So this calibrated file we will use for the georeferencing or auto rectification. Along with this GPS IMU file, we will also use the DEM data. The DEM data generated from the LiDAR. So we have a LiDAR. From the LiDAR, we can convert the LiDAR point cloud data to DEM. This DEM we will use for the auto rectification process. So after auto rectification, we'll get the scan length, georeference scan lengths, and this georeference scan lengths will stitch it to get the complete image of our field. After auto mosaic, so you can see the right side, the stitched, radiometrically calibrated, auto rectified imager. So now the pre-processing is over. So after the pre-processing is over, sometimes the spectral data consists of some noises. So we can remove those noises with the help of some filters. So you can see after noise removal, the spectrum gets smooth. And we can use the spectral data directly, or sometimes there are indices are there. You can use several indices for based on the application. You can see the vegetation indices that we calculated. So now after the pre-processing, then start with some of the analysis. So the analysis is same for both, whether it is from a satellite data or a drone data, most of the analysis is same only. So here I'm just showing the basic analysis that we are carrying on the drone data with the help of the NB image processing software. It's a powerful image processing software, not open source. We have to purchase it and then we have to use. So I will just show some of the basic steps. So this is the UI interface of the software where we can just, with the menu bar on the right side, many tools are there. We can file open, just we can open the file. Visible, it will load in the RGB. So not only RGB, the true color composite, we can also open in FCC, false color composite, where in the second case you can see the NIR, more reflectance for vegetation, then we will assign to the red band. So we can, it's clearly visible, all the vegetation part. So you can see the water body, the algae part is also there. It's clearly visible in the second case of the FCC, where the algae part is more clearly visible in the red color. But in the first true color composite, almost same. You can see the almost green color edges come. So like that, based on the application, it's always better to work with the false color composite for clearly discriminating the different algae portions in our water body. We can also open both together and do the analysis in multiple views. It's also available in the NV software. Then this is how we are collecting the spectral signatures. So you know, the UAV imagery consists of pixels. Each pixel have the spectral data. So we can collect the spectral data. Just click on each pixel, it will show you the spectra. So the first imagery, you can see the spectra, the blue color of the water body, then the vegetation green color, and also the soil. The second imagery is from the NEPA field, the wheat field in IRA campus, New Delhi. So there also you can see the vegetation spectra and the soil spectra. So like this, we can, by single click on anywhere on the image, we can generate the spectral signature of that particular region. Instead of a single click, you can draw an ROI, region of interest, where you can generate the spectral signatures. So here I draw a few ROIs for the vegetation, soil, water body, and algae. Then we can take the mean. So now it is showing the mean of the spectral signatures. So always better to take the mean instead of a single click. Okay, so you can collect as many as pixels and you take the mean of the spectra, then you can use for the analysis. So after spectral data collection, there are many applications are there. You can classify the image, or you can go for a regression. You can go for a prediction of some biophysical parameter or some the water quality parameters like that. You can go. So I'll show you. This is the spectral data collection for each pond. So this is a pond. You have 5 ponds in CIPA campus. So from each pond, I collected the spectral signatures. So you can see the spectral signatures are not same. So it means that there is some difference for the water in each pond. So like that, you can also collect the spectral data from wherever you want and you can do an analysis. So water not always shows the same spectra. So there is some difference. You can see the DOL, pH, alkalinity, that's also varying. So that may be the reason. So based on that, we can go for the predictions that I will show in the coming slides. So apart from collecting the spectral signatures from the imagery directly, with the help of a non-imaging spectroradiometer, we can also do the spectral data collection. The left side, you can see this is how we are collecting the spectral data. And with the help of the NV software, you can collect that spectral data into a spectral library. So our objective is to create a spectral library of few features in our imagery or in the study area. So after spectral data collection, we can go for classification. So classification means just grouping the pixels based on the similarity in the spectral features. So classification is of 2 types, supervised and unsupervised. In supervised classification, we are supervising, we are providing the data. So based on the data provided by us, they will do the classification. So here I have given some. So in this software, there are many super classification techniques are there, like SVM, ANN, most of the machine learning models are also there. So you must go through each model, you must learn it, what is actually happening behind each tool. Then based on your application and the literature, you can select a classification technique for your study. So here I used, I think, SVM, and I did the classification. You can see the soil and vegetation in the first map is clearly classified. In the second case, you can see the algae, water body, soil, and the vegetation also clearly classified. Apart from supervised classification, you can do unsupervised also. Suppose you don't have the ground truth data, you don't have anything, only the imagery. Then just give the number of classes you want. It can be 2 class, 3 class, 10 class, and just do the unsupervised classification. It will give you a classified image. After getting the classified image, then take the imagery and go to the field and do the sample collection. Assign each class to a particular feature. Like that also you can. So there are different image classification techniques and approaches are also there. In first is unsupervised classification, then supervised with the help of ROI, the training sites. The third is spectral angle mapper, where we are providing n-member spectra. So based on our analysis, our application, we have to choose a best approach for doing the classification, whether you have to collect the data from the field or from the imagery directly. Like then you have to pick. And after classification, NV is also providing the classification accuracy assessment, the help of kappa coefficient, overall accuracy. So always we stick on to overall accuracy more than 80% is accepted. So like that we can check the accuracy also. So another thing is indices, spectral indices, vegetation indices. It's very important in the context of agriculture. So in NV software, it is provided, there's a spectral indices calculation tool is there, provides more than 20 to 30 indices is available. Other than that, there's another tool called BADMAX, where you can type the formula. For example, I did the NBVA. You can see B1 minus B2 by B1 plus B2. So B1 and B2, we can assign to a particular bands. So like this 2 ways, we can calculate the indices. See, these are the indices that are calculated for the drawn data that we collected at 2 different sites. The NBVA, SAVI, images, and you can see the formula also. And also with respect to water, also there are many water bank index. Is there 900 by 970 nanometer. This index you can use for segmenting the water area. Okay, so in that index, you can see the algae part is not covered. So it will segment all the water area. Then after doing this classification, so this spectral indices, you can export this into a boundary file. Then you can clip your study area. So these are the few applications of using spectral indices. And other applications like for mapping the chlorophyll content. For mapping the chlorophyll content, we are using more than about 61 indices. So we'll just run the 61 indices. We'll get the 61 maps. Then out of the 61 indices, we select few and do some regression model. So sometimes there will be noise also because due to the presence of the atmosphere. between the sensor and the target material. Sensor inherent noises will be there. So you can see the noise in the spectra. You can remove those noise also. Some noise removal filters are also available in this software. After running the tool, you can see the spectra with smoothen. Then you can use that smoothen spectra for your analysis. So hyperspectral data or hyperspectral remote sensing is a big data issue. So always consists of more number of bands and very high spatial resolution, very large file size. So we always, for fast computation, for operational delivery of products from the hyperspectral data, we have to reduce or we have to make the process fast. So there are some dimensionality reduction techniques are there. Dimensionality reduction techniques means in the context of spectra. For example, in our case, we have 269 bands are there. So no need to take all the 269 bands. We can reduce the number of bands. So we have to see which band is needed or important for our study. So for that, there are many techniques are there. Feature transformation is there. Feature selection is there. Feature selection means selecting few bands. Feature transformation means we are transforming from that particular dimension to a higher dimension. So this is one particular feature transformation technique called MNF transform, where you can see that for 269 bands, after transformation, we'll get the same 269 components. The first few bands only consist of the information. The last band, there is no information. So like this, we can select the first 10 bands and we can do the analysis. No need to consider all the 269 bands. The advantage is we can make the process fast. We can get the data in an operational delivery basis, and we can use for the nutrient and application, all those type of analysis. So this is n-member extraction. Sometimes there will be mixed pixels. Okay, so especially in the case of satellite data, where the spatial resolution is very low. So this is a data of 30-meter pixel size. So there will be more than one feature in a single pixel. So in those cases, we have to extract the pure pixels. So the NV software is providing a tool called n-dimensional visualizer. You can see we are just plotting all the spectra. For example, we can select the number of classes. I just select 3 classes, and all the pixels I just plot in an n-dimensional visualizer. So those pure pixels always follow the extreme end. It will not fall in the middle. It will not get mixed up with the all. So you can see the extreme pixels, 3 colors, red, yellow, and green. Red and green. These 3 are extreme pixels. They are pure pixels. There will not be any mixing up of any other features. So like that, we can extract the pure pixels, and those pixels we can use for the analysis. This is called n-member extraction. Spectrally pure pixel extraction. So in NV, by including all these steps, the MNF, PPI, ND visualizer, spectral analysis is a classification techniques. So single tools are there, including all these steps. So at a go, we can run this by just giving the input data. By clicking the next like this, it will continue from starting from the spectral data reduction, then spatial data reduction using PPI, then n-member extraction. After extracting the n-member, we have to classify. We have to assign the n-member to a particular class. For example, one group of pixels to vegetation, one group of pixels to water body. That is n-member identification. And finally, classification. So this, with the help of this tool, all this the step-by-step analysis we can do an active. So after the classification is just prediction. These are 2 major applications of the hyperspectral data. So when it comes to prediction, there also we have to go for feature selection or feature extraction. Mostly we will go for calculating the vegetation indices. So you can see that we generate a leaf nitrogen concentration map with the help of the vegetation indices. Where more than some 61 indices we selected, and based on some criteria or measure, you can use R-square with a threshold of R-square 0.7. Those indices that falls above 0.7 you can set. Or the latest, the new technique of VAP scores. Those indices having the VAP score greater than 1 also you can select. So like this, by keeping a threshold, we can select the features, and then you can go for prediction. Prediction is like classification, same machine learning algorithms you can use, or empirical models you can use, or nowadays people are also using deep learning models. So like the based on the application, if you want more accurate results, go for machine learning and deep learning techniques, and you can get. And the right side, you can see by using a single band value, I estimated the pH and TDS. So from the literature, I understood that all the 269 bands are not required. A single band is required. So how we can get that single band is we have to do a detailed study by using all the bands, and finally we reach at a single band. So with the help of single band, it is showing very good R score of I think 0.7, more than 0.7. So like this, we can select a feature, then we can go for a prediction. So these are the basic analysis that we are doing using UAV hyperspectral data with the help of NV software. But mostly we won't use NV software. We have our own tools. We have developed tools using MATLAB, Python. For example, as I told, for nitrogen estimation, we have to generate 61 indices. So one by one, it's very difficult in NV software. So in those cases, we have our own code to generate the indices.
Just a bit confused, like index, what you were talking about. 60, like he said, like for nitrogen 61 index has been developed. So but this is for crop, isn't it? Now for example, when you go for fish, we have to develop it by ourselves because we don't have like softwares, we don't have data banks from which we can take. So it has to be done from the field level, correlating with your images. Is it like that?
Making one of the data to quantifiable indicator. Indicator
Yes.
gets that.
Yes.
That may be ratio or normalized ratio.
Yeah.
On band by ratio of other band, ratio index.
Yeah.
If you normalize, that becomes normalization. And that is with respect to the domain expertise you have or the cross or control to indicate so many indexes, 150 indexes in now. That's all. Suppose water related indexes you want to work or the phytoplankton. For example, phytoplankton. I have shown also here NDVI test. NDVI number is different, which is nothing but the rate band and near rate band is the 690 where the chlorophyll absorption takes place. So if there is a phytoplankton, chlorophyll is there, so there will be absorption. And with highly importance because again vegetation cells are there, for example, phytoplankton. So NDVI value will be good, very good, not as vegetation, unlike as vegetation in the water. So that's what you can indicate. Based on that NDVI, you can know pure water, where the pure water with the surface with algae or phytoplankton surface. So this is one index which is works for the vegetation and also for water.
Yes.
Same also for water turbidity. For example, water turbidity, there are some sensitive indices, like I have shown you spectrum where sensitive bands are there for seed going, colored digital oxygen matter, digital organic matter, like TSS, like many other parameters, for which you have the exposure to see which sensitive bands are there for developing the indicator. So you can develop index, go for the predicting developing equations. If it works, you can do for mapping.
Yeah.
So there are, if you look at the literature, there are indices for the water study.
Even for the fish also, like you study for the spoilage condition.
Yeah, that is, I was just coming to that. But yeah, right. Yeah.
For spoilage condition and also for the delay and how much time you can get to know, and using the hyperspectral images. Okay, for hyperspectral data.
Yeah, regarding the spoilage, actually, I would have come to that because there is a problem for fishes particularly because there's a thermal, there is a difference in a frozen spoiled fish and a fresh fish. Yeah, so that temperature is going to affect. I think that is what you call noise, or I don't know.
No. That is
Yeah.
not.
That is different story.
Okay. That is more on the
Yeah.
But if we have detailed study, now it's detailed. there's a big team working on this. Our expertise is there available throughout them. And yesterday they got a best paper award for that work. They did work on that for Pune. So, but we are doing it both hyperspectral, RGB, multispectral, and also thermal. So we are able to see the differences with respect to the coin and
So, and that is what, and the data points who are doing, they are doing in their lab. They are doing in the lab. And they are correlating with your like light reflectance.
a lot. For example, this is there, you can put the sensor, fish will pass through.
Yeah.
More time you can know whether this fish is good or bad. How much age is this? How much soil is there? So you can look at the feet, you can look at the tail side, you can look at the eye. So all those things are taken. We are on the study now. And we are not expert. You two are expert on physics. But we are the expert on the spectrum. We are trying to do those. But that we can discuss later.
Later, you're right.
So any question? I didn't think. I just said low hanging fruit. What can be taken?
One question to you. You mentioned about the soil parameters and vegetation parameters. Okay. What is your feelings? For soil quality aspects, your multispectral camera is quite good.
For soil quality, multispectral, no good at all.
Oh.
For vegetation, it is good. You
Okay.
can work.
Okay.
Soil
Okay.
multispectral never we work with. We are working with hyperspectral.
Hy-
That too, MIR spectroscopy.
Mass.
Starts from MIR spectroscopy, 1000 to 2500.
Mhm.
There you can get much better predictions. We have different sensors evaluations we have done.
Mhm.
So MIR spectroscopy, then DNR spectroscopy, then fluorescence spectroscopy. So MIR spectroscopy looks to be much better with a good accuracy.
Mhm. Another one is China was facing problem regarding the clear water. She couldn't manage that regarding vegetation cover and area mapping. And then how it was solved when there was gap. That part how
So
it was
that is
managed.
still a challenge. I
Mhm.
don't know whether Amrita, could you cover that?
That slide again?
No, did you cover that?
Yeah, that slide I told about
Yeah.
the issues.
Yes, yes. Yeah, that part ultimately what was made. I mean, how you got the picture. I mean, that part was missing. That parts were missing in China's figure. She couldn't do it. How
No,
you
that is
manage
not
that thing?
possible.
Here
So
also it is missing.
here is also
Missing.
here is
Uh-huh.
also missing.
Mhm.
So that's what we are working in. Any commercial software, they are not able to come out with the solutions.
Mhm.
If at all you have pure water body, you are getting the blank spaces.
Then we will not be able to go for any water
That's
quality
what I'm saying. Please hold
parameters.
on. That's what I'm saying. We are still working on that.
Mhm.
The commercial softwares are not able to address that problem.
Okay.
For that purpose, we need to understand how the images are stitched together.
Mhm.
When you take a raw image, the image is there.
Yes.
But while stitching, they are not able to.
It is
stitch.
not taking. Yes.
So what is that happening? It's like when you do a tailoring, you do a stitching, overlaying one over other.
Mhm.
Then you go for stitching.
Yes. Yes.
Like
Yes. Yes.
all this close. Same also in case image. When you
Mhm.
go for stitching, we go with a 70% overlapping when you have a multispectral camera.
Mhm.
When you have a like RGB camera or hyperspectral camera, also RGB also almost 70% overlapping, 70%.
Okay.
So that it get a
Mhm.
wonderfully stitched. When you do hyperspectral, 40% overlapping.
Mhm.
The problem in both the cases is altogether different. Different is that in case of multispectral or RGB, why you do 70%? It goes for finding similar features in both the images, similar features. Like
Mhm.
this bottle,
Yes,
this
yes.
bottle.
Yes.
So these are the tie points. Based on that, it will start registering.
Mhm.
It doesn't look for the location, GPS location. It looks
Oh.
for the tie points. So it creates a cloud data points, huge cloud data points.
Mhm.
Then it looks for that. In case of pure water, in case of terrestrial lands, you have features.
Mhm.
You have a
Yes,
leaf, you
yes.
have a plant, you have something. But in case pure water, that is always, there is no variations.
Yes.
So it's not able to find out the tie points.
Mhm.
Since it's not able to find the tie points, it's not able to stitch, that's why it's blank. So this is what the mosaicing, the stitching process, what these commercial softwares are doing. So instead of doing that, we should do something else. That's what we are working.
Yes.
We are in the process of doing
Mhm.
and come out copyright. When you do hyperspectral, it doesn't do tie points. It does based on the stitching, as I say. You go to any commercial software like image processing satellite data, there are water bodies, but they're based on the GPS training site points, we go for stitching.
Mhm.
So that's the reason why in water bodies, we use pre-processing. There are two commercial softwares called Pix4D and AgSoft. So those two commercial software fails to do this. We have been trying hard for almost a year now, but now we are trying to do in our own way, stitching them come out. You might have seen one area of our campus. There's a big 2.5 acre, 5 acre.
One.
Amritsar. They are stitching was
Yes.
good.
Yes. Yes.
And there are some fields in case of SIFA, in case of your wetlands where we have flown hyperspectral, it's wonderful.
Mhm.
But multispectral, you have a blank space. So this is the unsolved problem till now. So we'll answer it.
Okay.
One submission.
Sir.
We have been working on development from India.
Sir.
Unlike wetlands, where magnetic groups are there. So the spectrum would be very clear that completion highly profile character, a deep greenish color, deep bluish greenish color. But so far as underwear is concerned, it is very faint, pollution is very less. In that case, the greenery or that spectral, hyperspectral imagery indicates that how far the differentiation, some pockets, there are some groups are there. So how it would be clarified to your engineering professors and all,
since long I have been listening today, that we delineated that in these pockets, there are matrices low. And in that, if I look at diagrams, they don't populate that much of color in the water. That that's not the way one issue. Then give the clear water. For example, algae is there. It is what is that even so far as our chemistry is concerned, 0.001 nitrate or phosphate, something like that. So and how to differentiate? Any work done so far or yet?
Yeah, so for that, the solution is again hyperspectral. I have shown you two slides where people have done with the Hooghly and Haldia. We have done for airborne campaign, which was flown around 3 kilometer height, having the data from 400 to 2500 range. And we have calculated the properties of water, that is called inherent optical properties, IOP, and also apparent optical properties. So based on that, one can characterize the sensitive parameters like this. And there are a lot of studies. Because of time, and I'm not the expert to talk, I'm not a water scientist. So there are many research papers. That's what people have been working and characterizing them. Even if we are targeting to go for the microplastic also, in case of water, what we have. We don't have understanding much, but we are able to do some low-hanging fruits, like I say, phytoplankton, chlorophyll, and all those things. But there are expertise available in India itself to go for detailed minute studies of water. What do you say, in the PPM level also people are doing. We have as I was saying, I am a part of again, bigger team. We had a NISA. I had a professor, Sambungam, his slide I was showing. He is an expert on ocean optics. He is in IIT Chennai, upgrade on those fields. He has done wonderful work on all those properties. And there is another instrument called in water spectrometer. And very soon I am getting that instrument to you. That is purchased under my program, is given to IIT Kharagpur. It's still with IIT Kharagpur. Once this director goes, I'm going that instrument. The theory is now. Once he goes, then I will get back that instrument to here. So that underwater properties you can capture. Like you have a spectrometer, as I was saying, soil and crop. Water properties also you can do using that instrument that goes inside the water. And you can do all those properties. More data.
Why I'm so much interested because last year there was a huge loss to results to remember in Jharkhand. Source of cookies species died because of ulcer eutrophication. And already that result is already eutrophied, and they are doing what is that protein pen where lots of things being loaded. So that eutrophication and it gone to ulcer eutrophication. And finally, what happens that dial variation at daytime the oxygen goes beyond the PPM 9 it goes
in 9 presentation, I told you something.
So
I'm coming back to that. I told in my presentation, there is a diurnal variation of oxygen level, and also there is a seasonal variation of oxygen level.
Yes.
So that diurnal variation of oxygen level, one can do based on that phytoplankton what you have.
Yeah.
The way they grow, and based on that oxygen level, the consumption and carbon dioxide, whatever. So based on the phytoplankton, you can go for dissolved oxygen also monitoring as a surrogate parameter. So you don't need to have a dual sensor in water. Rather, from the sensor up on the sky, if at all you have every 2 hours, 3 hours monitoring, you can do that. And that is what the possibly next paper we are going to come out with SIPA is that one. So we have a control smartphone inaugurated by Honorable DC back in July in the SIPA. So that is where purely totally erosion is proper. Another, we are allowing it not to have erosion. Peace is going to be there. So 2, we are going to monitor. Do the imaging to do all those studies what you want. Raise a question. Any question? Then we go to
I have another one.
Yes, sir.
You were telling about the pH and other parameters. Is it really related to your spectral things?
pH is get affected because of some chemical properties.
Yes, it is true.
And that chemical properties allows that also affects your radiations coming back. So this is a basic fundamental behind it. For example, as I say, surrogate parameter. Based on the phytoplankton or algal growth, your dissolved oxygen is going to change. Diurnal change is why it's happening. Because of light condition, entrapment and better growth, and then oxygen level goes up or goes down. So that same also with respect to pH. So there are sensors
by which you only measuring the pH EC, you can go for automation of alkali and pH level monitoring or inserting some chemicals to maintain the neutrality or pH level what you want. That is what a sensor we have in the vertical farm. We have, you can come and see, we have hydroponics where the only measuring the pH EC, they're going for fertigations. So once you measure the EC and pH, indirectly you are able to know how much the solutions pH EC level is changing, maybe because of what. Already we know because that's a standard water, standard nutrient which is applied to. So based on that, again fertigation is done. In our
We'll have to read. We'll have to read and.
If what you want, like under this program to see how that's what my team of 5 experts under working. They're all experts.
After this hectic day, this is the end, last class, last session, sir, actually. And in this, actually, the topic provided to me was the drone-based spraying in field crop as well as the fish farm, and its opportunity and challenges. In the first lecture only, the director C3 has mentioned a lot about the different opportunity and challenges in the especially in the fish farm. So in my presentation, I will concentrate mainly on the drone-based spraying in the field farms. As most of us we know that there are in the initial sessions there was one somewhat it came that
the drone is also used for the surveillance purpose. I think Samantha sir was telling, I think. So sir, there is a lot of drone also, and during the surveillance drone, the main thing is that as we move up, the field of view will increase and the more area it will cover. So in this case, mainly in the surveillance drones, sir, there is a wired drone that it will go up to 400 feet, 500 feet, and there is a regular supply of electricity and power to the drone, and it will hover for a uh, in a alternate basis, 8 into 3, it will 24/7, it can surveillance for a particular area, high, especially high value area, sir. So in that case, because the most of the drone in our country, and even in the broad, sir, in the power operated, we have also seen and tested the gasoline operated, but it is somewhat, it was not successful because it produces a lot of sound and other things, gases also, so carbon dioxide also. That is not very much useful, especially in the metropolitan cities. So most of the drones are the battery operated, and the operational time is varies from 20 to 30 minutes, maximum 30 minutes. So these drones can't be used for a surveillance purpose for a longer time, but for that there is a wire type connection for the continuous power supply. So here the drone based spraying and sampling, there is a basically a spraying drones, what we have seen today. And the CIFRI already has the broadcaster drone also, that can also be used for the, as our directors are told, that it can be used for the feeding purpose and to the fish. The water sampler drone, the CIFRI has made and already patented the sampler system. In this water sampler system, it will go up to a certain depth, and at different depth up to 10 meters also it can go, and it will take the samples mainly in the inaccessible area where we can't go very easily. And in the initial session also, there was a underwater drones, that is ROV, that is sonar based system. So the range of this is not very far, but it can be used for the certain purpose, monitoring purpose of the drone fish movement and their activity. So these are the there are other type of drone, that is the multi-utility drone, that can be used for the actually Saucer has not covered. There is a 5G drone that can be has capability of inbuilt data analysis, that is called edge computing system it is having. At the same time, it will analyze the data and give the output accordingly. You can give the management practices. So these are the different types of the drone. Here, what the government of India has taken the initiative regarding the spraying drone. The government of India is giving a very much subsidy to the farmers, especially 50% subsidy. It is written up to 5 lakhs to the custom hiring centers. Where if anyone very interested, they can avail this one. 40% subsidy up to 4 lakhs for the individuals farmers. Actually, belonging to SC, ST and the small and marginal farmers category. And Krishi Vigyan Kendra, they have given facility, they can acquire that drone also, and they can also have a good amount of subsidy. And under Digital Agriculture Mission, there is a it was launched by the Ministry of Agriculture, and in this mission also, the farmers and the beneficiaries can take the advantage. And Kisan drones, as we all know that the every KVK, most of the KVK has given a Kisan drones. It was launched in 2022, and in our institute and most of the ICAR institute has got the Kisan drone, and it can be mainly used for the demonstration purpose and to familiarize to the farmers as well as the youth, especially that those are in the village area. So these are the government initiative. And this is for the spraying purpose, and for the researcher purpose, the individual institute are coming and they are taking its own way. We all know that this is the application of the spraying, that is, we can spray pesticide and fertilizers, nano fertilizers. I will show a case study of the nano fertilizer, how it will be effective compared to the knapsack spray through the donors, compared to the knapsack spray. And the herbicide and growth regulator, especially growth regulator, like gibberellic acid, can be broadcasted to the in the grapes and other crops. That can be also very much useful. And this for the orchard, where you can't go and from the ground, it will be very difficult. In the orchard, it will be very efficiently and effectively you can spray the insecticide and pesticide. And the benefit of the spraying drone, we all know that it is very much efficient. 20 liter or 10 liter 10 liter 10 liter is sufficient for 1 acre land. Almost 25 liter is for 1 hectare land, and it covers inaccessible area, as you know that, and very fast also. It is cost effective. We have also calculated the benefit cost ratio of the spraying drone, and it is coming relatively less to the knapsack sprayer, and eco-friendly. If you use the drone very as per the guidelines, then it will be very much eco-friendly, because there are certain limitations also. Using that, under that limitation, you use the spraying drone, that it will be very beneficial. And the precision, actually ultimate goal of ours is to develop the variable rate applicator. That means where the actual requirement of the pesticide or insecticide, there only it will spray, otherwise there is no spray. So in that case, there will be efficiency increase, and precision will be there will be very much precise application, precise and localized application. So these are the different parts. Today you all have seen the spraying drone, and most of the ICAR institute and KVK is having the spraying drone. There is no need, and the different payload. Here the payload, in our case, the payload is the sensor. Here the payload is the chemical amount of the chemical. So the different less than 5 kg payload is available, 5 to 10 kg, 10 to 25 kg, up to 25. So somewhere we have seen that up to 40 kg chemicals having the payload capacity drones are available. Number of the propeller, it is quadcopter and hexacopter, depending upon the payload. But we have seen quadcopter also, but hexacopter we will recommend for the hexacopter, because if one propeller in somewhat miss, then by that time it will reach to the landing point. The nozzle type, it is very much important, mainly the flat fan. Today, whatever you have used, that is the cone flat fan nozzle. I will show what the flat fan and cone shaped nozzle, and there is one is the centrifugal fugal type nozzle. So these are the here this is this is the flat fan and cone type nozzle. So you can see how the spraying of the flat fan and cone fan nozzle. In cone fan nozzle also there are solid and hollow cone nozzle. So these are different type of nozzles. Depending upon the nozzle, there the flow rate is varying. So flow rate in the drone, whatever we have seen and we are using it, varying from 300 to 600 milligram per minute per nozzle. And operating pressure of the nozzle is around 3 to 5 bars, 2 to 3 bars. And this is very much important. As the pressure increases, the droplet size of the spraying material will be vary. Higher the pressure, lower will be the droplet size. So droplet size, volume, and uniformity we have to test before going for the actual spraying. And the operating speed in general, we apply the we fly the drone at 4.5 to 5 meter per second drone speed. And during the launching and RTL, it is not very much important, but it should be very relatively higher so that the wastage time should be less. Already 10 minutes, in 10 minutes it will cover 1 acre land. So relatively very much fast it is. And spraying height, it will also vary with the crop to crop. And it should be 1.5 to 4 meter height from the canopy, higher top of the canopy. And if the crop is prone to lodging, then the height of the drone should be more because it will produce the lodging effect because of the thrust, the drone. So thrust is mainly if the any drone hover or fly, so thrust, especially when it is moving, then the thrust is more than twice of its own weight. If suppose there is a 25 kg drone with full payload, then it will produce more than 50 kg thrust. So 50 kg thrust, if the crop is at the seedling stage or if it is in the irrigated condition, then in that it is preferred you should not go for the drone spray. And dynamic thrust of the drone. Actually, as you know that I have already told that the thrust is about 2 to 5, 2 to 2.5 per times of the weight of the drone. So drone, when you start the spraying the drone, the payload is maximum. So thrust of the drone, payload is decreasing, then thrust of the drone is also decreasing with the same speed and same height. So there is a decrease in the thrust with the tank. If the tank is empty, then the thrust will be less. And one more thing I would like to say that in drone, most of the drone, the 40% weight of the drone is battery and 40% payload, and rest 20% or almost 20% is the actual drone weight. The drone weight is as such nothing, very less. But battery, in the previous class, Pratim was telling that the lead battery and some efficient battery is coming. So less weight, more power or more time, more durability and more power battery. Nowadays it is coming. So here this is the environmental parameter what we have to consider before actual spraying. That is the wind speed is the one of the most important. That is the recommended limit is the maximum 10 kilometer per second. If you convert it in meter per second, it comes around to 3 meter per second. 10 kilometer per hour, it will come 3 meter per second. So 3 meter per second, if the speed is more, then you should not go for the spraying. Especially in the coastal region, the speed of the wind is relatively higher than the mainland. So in that case, this is a challenging task for the spraying purpose. And the impact, only the drift is the main impact. So drift, we should not spray to the other crop or adjacent area. So in that case, should take care of the wind speed. And the second is the temperature. Temperature, it is not directly related, but somewhat it is very much important because 15 to 30 degrees is recommended from the textbook we have taken. Because if the temperature is high, then and you know that in the later slide we will tell the droplet size of the drone is relatively very less. If the temperature is high, then it dry in the air. In that case, it will not be very much effective. It will, in the form of powder, it will fall on the leaf. So this is one of the parameter. And the third is the humidity. So temperature, humidity almost the inverse. So humidity should be more than 50%. If the humidity is high, then if the humidity is very less, suppose, then again it will dry in the air. And if humidity is very high, suppose 90% humidity, in that case, leaf is also wet and it will fall on the leaf and it will take time to dry. And the foliar spray, it will go through the leaf of the plant. The chemical go to the plant, the leaf, through the stomata, and it will take more time. So there is a upper limit also, and there is a lower limit also of the humidity. And the time of the day, at what time we should spray in the morning and evening, you have to spray mainly during 8 to 6 to 10, 6 to 8. And one more thing, in the morning time, only morning and evening, the same time, the pollinator, what we say, that the bee activity is more. So if there is a, at the flowering stage, the crop is at flowering stage, then it is just strictly prohibited, because you are just, there is a two-way harm to the plant, to the plant. One is there is a loss of flowers also, and there is a loss of honeybee, bee and others insect that helps in the pollination. So in that case, this time of the day and time at what time we should spray, you have to consider. The crop stage is one of the other factor we should consider. If the crop is relatively lower stage, then the volume of the spray will be less, and if crop is under full grown, then it should be more. And the time of the type of the chemical, almost there are 39 chemicals that we are for the agriculture purpose through that road. But SOP yet to be established or released or somewhat. There are very much research is required to develop the SOP and say that this chemical is most suitable or suitable for the drone spray. Still, we are spraying the chemicals that are we are using for the knapsack and other manual sprays. Suitable time schedule that is covered, I think. And length of buffer zone, that in general for the crop area it is 5 meters, and for the water body it is 50 meters we are considering. But first time we have generally we are spraying in the crop area, 5 meter buffer zone we are creating depending upon the wind speed and height. It will vary with the height also, but in general we used to fly at 3 meter height from the canopy cover. Technical parameter what we should also consider, that is the droplet size. Droplet size, as I told, that it should not be very less, but not very large. If it is large, then there will be no advantage or no benefit compared to the knapsack and handheld spray. So in knapsack, in generally more than 600 micrometer is the droplet size. Here in case of drone, most of the spray, although it will depend on the nozzle type, but in any case, what the nozzle is used for the drone spray is coming under 600 meter droplet size. If droplet size is very small, in that case, if the droplet size is small and relative humidity high, in that case, it will not settle to the leaf of the plant, because the terminal velocity of the droplet is very less, or it will suspend in the atmosphere only. Then again, it will be not very useful to for the spray. And droplet type of we told spray uniformity. There are different factors we have to study, and we are actually studying in the IRA wheat field, wheat and rice, that how uniform the drone spraying is through drone spraying it is coming. Here, this is the aerial drone versus there is just a comparison between the conventional spraying and spraying through drone. Already I have covered it is quick, easy, and highly efficient, and no minimum operational exposure, safer to the one more thing, it is very much safe, because the drone you can spray up to 500 meter. It can go up to 500 meter from the pilot. So then you can spray up to 500 meter away from yourself. Then there is no human hazard, and it is very much safe. And one more thing that we also that the wind speed, against the wind speed, you should not spray. there is a saving of water also. It only 10 liter water is required to spray 1 acre land, 1 acre area. Whereas in case of normal spraying or the in knapsack spraying, it will more than 8 to 9 times. Minimum 100 kg, 100 liter of water is required to cover 1 acre land. So there are around 90% saving of water. And since the uniformity and other things are relatively high, then there is a saving of chemicals also. So there is a 10 to 15% saving of chemicals is also reported in the different studies. So these are the personal and safety equipment to ensure the safe. This is the most thing we have covered. There are a list of what we have to do, what you have to note to during the drone spraying. These are the list. Participants, we will provide the this slide or this manual. In that it will be mentioned. And these are the different research yet to be attempted and we have to consider. So first is the coverage of the nozzle. So coverage of the nozzle depends upon the first is the type nozzle of type of the nozzle and height of the nozzle. As the height will increase, the coverage will be more. But there will be no linear relationship between coverage and height because after a certain height, the droplet will fall under the free fall under the gravity. So it will not like that. So these things we have to consider. And there is the overlapping, how much it should be overlap between the two nozzles. Generally in today also you have seen that there is 4 nozzle in the drone. So the placement of the nozzle where it should be. So in today up to today itself the placement of the nozzle is not uniform and so that there is no uniformity in the coverage of the spraying. The arrangement of the nozzle needs to be rectified. Here there are 4 nozzles and you can see that the distance between 2 nozzles is not same. So then how you can say that it will spray the chemical uniformly and all the 4 nozzles are same. Otherwise you have to change the nozzle angle. In the market there are different types of nozzle. So then you have to calibrate the nozzle in such a way that the uniformity of the spray should perform. Here these the same things I was telling that the placement of the nozzle, it is very much important how the drone with the nowadays there are different type drones are also coming with the boom, and in this boom relatively uniform placement of the nozzle is placed. In this case there will be much more uniformity. Whereas whatever today you have seen the drone, in that there was be no proper placement of the nozzle. So there one more thing is the in flat fan nozzle itself center it will be more. The amount of chemicals or amount of water it is coming more, and with side it will be less. So again with the type of the nozzle, and you have to calibrate or place the nozzle in such a way you should also cover these things. So generally the linear placement of the nozzle, this is the study that how uniformity the nozzle is performing, that is called patternometer. Through that you can see how the with the distance and much chemicals it is releasing with the distance. So these things we have to consider before the actual placement in the of the nozzle in the drone on the drone. So one more issue, what I have already told, that the drift management. So drift management, there is a spray height above the canopy, higher the height of the canopy, more at the same wind speed, it will be more speed, drift, a speed of the drone, and the suitable nozzle and droplet size you have to consider. A buffer zone can be demarcated, and a spray schedule should be appropriate, and time gap. So these are the different things we have to already with this. So this is a case study what we have done in the IRI field in the wheat crop. In that we have tested the different, these are the uniformity coefficient, that is the number of droplet per unit area, the droplet coverage, coverage percentage, that is how much droplet is covering to the leaf, the droplet size distribution, how it is changing with the, we are telling that 50, 100 micrometer droplet size, 200 micrometer, but actually how much it is and what is the percentage of the each droplet. Then the volume medium diameter, uniformity coefficient, and relative span factor. So these things, these are the different evaluating parameters of the drone droplet and its efficiency. For that, there is a water sensitive paper. So we have used that water sensitive paper in the wheat crop at the upper, middle, and lower layer, and as well as in the knapsack drone edge, as well as in the knapsack condition. Springs. So here we found that the in case of drone spring, first is the droplet percentage is higher, and in the upper upper layer of the crop, that you can see here there are 4 bar diagram, that is depending upon the size. So the droplet percentage is more than 40% of the less than 150 micrometer, and then there is 150 to 300 micrometer, and thereafter 300 to 600, 500, and more than 450 and 450. So these are the droplet percentage, and these are the number what you are it is written. It is the number, actual number, what the number of the droplet of the water sensitive paper, and this in the right side it will be in knapsack condition. So how it is changing with the spraying type, and how it is changing with the upper, middle, and lower region of the plant. We have seen here. This is the coverage and uniformity coefficient also. So by observing this data, we are able to see that the uniformity in case of uniformity in terms of droplet size coverage, it is relatively higher in case of drone compared to the knapsack spray. And how efficiently it is going to the crop, and we are all telling that the drone spraying is beneficial to the crop health also. For that, we have taken the multi-spectral images, and through that we have calculated the NDVI. We have taken 10 days before, at the same day, and 10 days later to the drone spraying date, and we analyze how it is in the different field, how it is changing. So in this, we seen that there is a more increase in NDVI in case of the spray of the drone compared to the knapsack spray. So here, these are the challenges. The directors are already told that what are the challenges for the fish farms, but in the field crops, this is the first regulatory hurdles. There are different as tomorrow morning. Today morning, sir, Shimali sir was telling that if it is more than say certain kg drone, then it will be more than the traffic in the sky drone will be. So there is a certain regulation, sirs, that DGCA is giving. So nowadays there are very limited application. That's why it is giving to all. But if it is coming burgeoning condition, then certainly government will make certain changes in its current regulation, and it will be regulated. The drone technology adoption, and other challenge is the payload and battery constant. As you know that I have already told that 40% weight of the drone is the battery. So high efficient battery is required, and research is required in this way. Spray drift issue, there is a drift issue, and in somewhat the drone weight and drift is very much also. The drone company is telling that with the flattering effect, it will go to the lower portion of the leaf also. So they are telling that it is that this flattering effect is beneficial for the spring. So we have also seen that in the lower portion compared to the knapsack, it will be relatively higher than in case of drone. That is integration challenges that is contributing connecting drones, the IoT and the data analytics. Actually, our in this network program on precision agriculture, we are also trying to develop a variable rate applicator. It's not for the only for the fertilizer application, manual fertilizer application, but in the case of spraying also. So based on the requirement, and integration of IoT and other sensors, we will try to develop some arrangement so that the actual variable rate applicator can be developed. So these are the opportunity, enhanced precision. Precision with time, it will increase. Obviously, it will increase, and with the invent of this drone, spraying drone, the more precisely we can able to spray, and efficiency and the speed. Already told that it is very much efficient, and speed is very much high, and the cost effective solutions. These are the opportunity nowadays. Earlier the spraying drone was of 10 lakhs. Nowadays it is coming under 5 lakhs, and with time it is coming that within 2-3 lakhs it will come. Real time data integration. There is a opportunity in the same drone, the spraying as well as the different sensors we can integrate. But for the imaging purpose, the drone stability is very much important, where the company is not taking care of these things in the case of a spraying drone, because for the spraying stability of the drone is not very much important. So if anybody want to integrate this with the sensors and imaging purpose also, then the stability of the drone should be relatively more compared to whatever we are having at this time, and the safe operations, as we know that there is a very much safe. This drone spraying is very much safe. These are the different, the same thing here. It is the high initial cost. With time, government is providing the subsidy. So you can avail, anyone can avail. Limited awareness, then training programs and demonstration camps by the ICAR and KVK, and this supply private players are also coming. Regulatory compliance. Nowadays there are the drone rule 2021-22. It comes, and there is a lot of changes. It was made by the government here, and now DGCA and Digital Sky platform. It is relatively in last 2 years it is simplified, and technical expertise, the certification program and a skill development for the operation under Digital India initiative, it is going on. And there are certain troubleshooting in case of when you are flying drone, it will very much come. You have to go through, that is uneven spray coverage. So then there is a possibility cause that your nozzle is clogged. So then you have to clean the nozzle. Prone instability, then high wind speed may be one of the reason and low GPS signals. Then you have to suspend operation. You have or recalibrate the GPS. And there is a reduced spray pressure. Then the faulty pump. As I told that the pressure should be not less than 2 bar. So it should be minimum 2 bar. So you have to inspect the pump and refill that time. And battery warming in somewhat in the high temperature, low temperature, there is a limit. During that only the battery is operating efficiently. In that case, you have to replace the battery or give some rest to the battery. So these are the way forward. That is the policy framework, harmonized policy framework. There is a then the technology advancement. We already with that time it is in enhancement the technology that the SOP a standard operating procedure for the spraying drone we are trying to develop, and already some university has also developed, but it is a for a particular crop and mainly for the rice and some other crops. And some is the capacity building. We have trained a lot of youth and so that we can popularize the farmers. We can popularize the drone technology, especially to the farmers, and the collaborative research. As you all under this only you came here and be under the network program on precision agriculture. So we are taking care of 15 institute of ICAR, and here, so these are the different way forward we can look. Thank you.
Any concern, question, issues?
I have a question, please. You have nicely worked with the spray volume, droplet size. Actually, for our system, for I mean spraying purpose, what height we should maintain? I mean, which is better to have? I mean, it should not flow out of the system.
Yes, if you are spraying chemicals through water,
yes,
then it should not, and it will be low, then the drift problem will be less. If you are broadcasting, then there will be very less chances of drifting. Wind speed will not come into picture. So in case of our in the crop field, it is 3 meter to 4 meter.
Yes.
So below 4 meter, water body also is not recommended. 3 to 4 meter you have to consider, because water it will depend upon the pilot skill also.
Yes.
That you have to give some chance to the pilot, so that it is 3 meters. I think it is optimum for the water body also.
Sir, thank you for your lecture. I am again asking sir one practical doubt for me regarding that. While we are spraying because small ponds, we no need that much of drone application. There our farmers are doing. But if in large pond, when we are spraying, we are facing difficulties that we are need to be multiple refilling the container.
In case of spraying in the crop, it should be diluted. But I don't think you can spray in a concentrated form in the pond or in the water body. I think so. I have not done, but there should, if you spray in a high concentration on the plant, then there will be a burning issue. But I don't think if you concentrate highly concentrated chemical you are spraying in the pond or in the water body, it will affect, because ultimately it will
Diluting.
Yes, sir.
Okay.
Highly concentrated but I have just
No,
पढ़ा नहीं है nothing.
वो देखना पड़ेगा. And another one thing, sir, when we are spraying, suppose we are going to refill, so particular one area, then again the drone is returned back to our land, then we are refilling. then that is your previous one. Is there any sensor that we can mark up to that much area we have sprayed? Then again from there we can spray?
During the flight planning, you have to take care. From that only it will start next.
Okay.
So there is a provision.
When they're mapping that how much area if that time you have to put a drone of this much volume, if you cover this much area, then you come back. Next, when you are going, you start from that area and you go on.
Okay, that suppose drone is flying, still you have impedance, still you have liquid in the tank. Here it has sprayed, in between terrestrial land, nothing to do. Then it will go to that pond, spray and come. So that you can do beforehand. Actually, these are the boundaries. And it is a GPS guided drone is flying. So once it enters into the boundary, it starts spraying. Before that, it won't spray. There are also some drones with avoidance mechanism, like you have, like in case of crop field, you have crop field, immediately there is a building inside, or some tree, orchards are there, you don't need to spray. You don't spray. You just put out that boundary. Once it enters, you don't spray. You can stop spraying. The common drones also, they have that. So this is possible.
Okay.
But within a field, suppose you want to put off and on, again, rate of spray, that's a challenge. But I don't know water body whether rate of spraying is going to different from different places, that I don't know. In crop, it is a very challenging.
Thank you, sir.
Not that, because we calculate the volume on the water. There is no we calculate the medicine, how much is there, because 1 acre meter there. You are on the surface, we are looking, but we record 1 acre meter there. Now, sometimes when we are going for pesticide, antibiotics, that we for ton of this. Generally, antibiotics is not broadcasted in the pond area. Only those sanitizers, other things, they are broadcasted. And even if you go for the concentrations, just like CFAX is 1 liter, 1 hectare meter. So if you have, that will be very easy. Suppose you have a large 5 liter, 10 hectare, directly the raw form, you can put it and it will be diluted in this wind action, it will be percolated in the water. That is a thing. But in some other cases, if you have not, you can have the full 10 liters. Suppose you have a 1 hectare water bed, then you can dilute to the 10. And so if there is a wind action, other things it is there, or if there is aeration is running, you stop these things, later on you can give the aerations, that will be. So effectively we have to make some of the guidelines when you are going for different pesticide chemicals, how it will be, spraying mechanism will be held in this year, based on the situation.
And what that concern, please, you can repeat the same concern before.
No, on what sir that concluded, I would like to add to that. For what Saurabh was asking, that sanitizer and all, no issue. My submission is last 3 years, there was wheat fallow in Winnebago because of wheat smart. And this year, rice plus was the above. Patches of patches were burned because of rice plus. So in that case, using particularly using the fungicide, okay, insecticide is the one which is fungicide, second type. So in that case, for patches would be through JS mapping and to located to your hands and so on. But what you have been applying in that case, and wind action, another one issue. And in that case, how to configure these areas that whether the applications that being made exactly in those locations.
You see, suppose 3 meters where he is talking, you can come down to the wind action there, you can come down 2 meter distance where you don't find that much wind action will be happening. And the coverage you are spraying fungicide, all these things, it may be little way of maybe diagonally, you will see, diagonally spread something. Therefore, you have to mapping little 1 meter back, 1 meter forward. So that much extra area will take into the consideration. Yeah, that should be there.
While spraying, there are some standard SOPs. Those are the environmental parameters. Most important is the wind. Wind speed should not be exceeding more than 3 meters per second. If it is, you should stop spraying. So same also radiation. If a bright radiation sunshine hours, it's not allowed. You are not supposed to spray. Topography.
So all those things are there. So one has to be very careful, and if you go below a certain height, because of aerodynamics first, plant may get damaged. The flower may get damaged. So there are certain conditions for each crop specific spraying rules and norms are there. Coming back to rice blast, now we are working, 2 students are already working. One student is right now in US, our IRIS. We are doing early warning based on the sensor, same sensor we have been using, doing early warning. I think I skipped that slide. So how early warning you can do before visual symptoms, using the sensor signal what you receive from the visual, it's not the biochemical sensor already taking place. So you will get some signal. That signal is captured by sensor and you will be able to do early warning. And threshold, you know, what is the critical level. Based on that, you can go for spray. Challenge remains is you have a pest, particular suppose rice blast, another is BLB. The chemical is going to be different. How at a go you are going to spray? Yeah. So these are the all practical challenges. We know that. So both are mixed there in the field. How will do? Yeah. One by one has to do. And again, how much is the rate of spray? Somewhere it is severe, somewhere it is less. How to do that? And once infected means infected, it is going to infect. And you are spraying in this field very small, 0.5 acre. Another field is besides there. It is very healthy and it doesn't have anything. He may go sue a case against you. How come you are spraying in my field? So there are some challenges with respect to Indian conditions. One has to do for that. That's the reason for any. So right now, what the government of India has promoted is only uniform spray, but there is nothing called variable spray, which is must. That's what the concern is. And for that purpose, you should go for the remote sensing, crop health monitoring, understanding where is what happening. Then only you should spray there. So that's what the work's going on, right? So you want to ask?
Yeah. Actually, I'm just saying, quite interesting topic is brought out, and it reminds me of our tea plantations. You see, regarding early warning. So you're right, sir. Regarding once this helophyllates, red spider, all these things, they damage the crop. Once you go for visual inspection, because tea plantations, we have around 500, 700,000 hectares per garden. So visual inspection of all these things, it's very difficult. So what happens in the long run, once the leaf has been damaged, only then we go for the spraying. So this early warning system and the stress of plant, I think you're working on that. So, stress because of pest infestations, stress because of, say, deficiency of some nutrients. So those things you are working on. I think you have made some. Yeah, so that is one very interesting area we need. I think your help will be required in that. I think in tea, it's a perennial crop. It's a canopy crop. So, what kind of help you can give us in that regard?
Challenge remains is, as you say, tea garden is under the shadows.
Right.
So there is always a off and on light condition.
Right.
How to fly a drone with that diffuse light to capture the data? That's what I have not seen yet. Any tea garden. I would love to visit and see what is the mechanism we can. Or else we can have a robot which we have with us. Maybe we can recommend what kind of robot we can have. Canada also they have, in US also they have. So same also if we can go around and capture the data. Again, I mean, you have a satellite, you have drone also. We should find out viable low-cost technology which is. I spend 100 lakhs, but nothing is coming out because there are practical challenges. That shouldn't happen.
No.
So we should do something based on that. Another is, irrespective of the light condition, if at all I am able to get the pest and for example, today morning, someone remote sensing. Irrespective of light condition, it's okay. And thermal remote sensing is good also for pest conditions.
Yeah.
And that is again low-cost technology. If that can be used. Yesterday, day before yesterday, I was talking about acoustic. There are low-cost acoustic sensors available, and if at all there is some pest or disease, some acoustic signal is coming up. There are already people started doing research. If we can do that is second. Third is VOC, volatile organic compounds.
Right.
And if at all we can capture that volatile organic compounds, but they are going to be not that concentration, not that high to be sensitive to the sensor.
Right.
So there are some already sensors people have developed. Age Research Institute with us, one scientist, Dr. Subisi has done with the age and patented. So similar, I think somebody made a presentation.
I think
In the ANC also.
Yeah, yesterday.
So already people are working on those lines. So these are some approaches.
Like we need to sit down to see what is the viable options for you to make it a operational scale.
Yeah, it'll be taking some time. Okay, thank you.
And we'll compare with the agricultural application and aquaculture or fisheries, it's a totally different. It's a totally different because for sanitation, other things we treat the water. Again, for if individual bacteria, that we treat the fish. So there are two way of, and for that only they treat the water. So we do not require just like agriculture, the intensification of the infections, all these things. Generalized system, sometimes we have to, within, just say delivery 3 days, 5 days interval, second dose to ascertain your infections rate is reduced. These things we have to adapt. Then it will be happening. Because you do not know, the boundary is not defined because they are moving swimmers. But crops is a static,
right.
And fish is a swimmers. So you don't find a boundary is there that where you can only go for the applications. So that is one of the another aspect when you are totally, again, we do not, even if visualize, you see, we have it like the previous estimation. Now if you have a underwater robots which can estimate how much fish is there, or satellite sensing how much fish will be there. Then you can see the number of biomass, then your treatment will be initiated. Or as usual, just like your cast nest, nest. If you don't have that much system to take a cast net, find the square meter, how much fish is there, calculate per hectare how much fish, the usual traditional way of estimating the fish. Then you have your treatment starts. Use the latest technology if you do not have that much things, because reaching to everything, integrating it, all the technology may not be with us. Whatever one or two technology with us, we should start working on that, mixing the other technology. Then it will be successful. So that's when or else will tell that you have learned all these things, integrating will go. That will not happen for any particular time of it. Because it will not happen, because maybe a research laboratory may have that time, they will take all these things. But when go to the field conditions, establishing a field laboratory, because simple diagnostic laboratory has not been established in any district level, block level in fisheries. And if you think it is also, maybe another 10 years it will go, if you think a district level, because the officers, everything, all should be trained in all these aspects. That will not happen. But it can be happen only through network. It can be happen through today networking. Tomorrow if you want to build up a setup, because third thing is a manpower. You should not be certain that you will be all in one. So that is also things will come, but it is all ifs and buts. The private sectors is coming in a faster rate. Entrepreneurship is developing in a faster rate. And they will provide a hub to all type of things to, you can hiring center, everything that will help us for working on this thing. Definitely, maybe today the percentage usage is 0. Maybe 2 years you'll find it will be. And this technology, because this part of eastern part of our India is a traditional farming. Very few are semi-intensive, intensive. If you come to the evening part of the eastern, that is Andhra Pradesh, they have the modern practice, they can adopt anything. They can adopt anything, any technology, any levels. So that is the differences. So if you have a technology to showcase, go to Andhra Pradesh. Bhimavaram, Kolleru area, so technology will be effectively disseminated. This is that. Then if you come to here, maybe you will find very few people taker, but this is a sensitization method where these educations, research organization, all those things, and few entrepreneurs will be come forward to know the technology. But nevertheless, like you could see, you're like Medinapur area, other places, where shrimp farming is a big, or here you will find some blocks, 200 bighas, 300 bighas, they are going for a systemized culture techniques. There you can, this methods will happen, because now you have the area like Malda. Fish culture is coming in a big way. They are converting the pond means IMC culture, everything is a big. So the technology is required. They can accept the technology, it can be implemented. So these are the newer places bringing into the aquaculture innovations. The technology adoption is because you can formulate FAO, APO, then ask for the government to funding or subsidized systems, then they can adopt the things then. So that is this maybe for in fisheries and aquaculture point of view, though it is a nascent stage, but maybe within 1 or 2 years it will definitely pick up, because even if government of India is pushing up, because this is a Prime Minister office, the things are coming to implement this. Maybe your bankable scheme, everything will come, a large number of people. So prior to that, we should be strategy and preparedness. Each of us should know these things, then implementation will be very easy for all of us. So that's why this training is, I think it is informative for all of you. And anything if you want, you can ask those people, not in CIPRI, across the IRE teams anywhere, they can ready and come forward to this. Particularly when you ask Dr. Sao, he is all the 24 hours. If he is busy, he will not give you any reply. When you will free, call back to you and solve your things also. So that is the most way, because your KVK is a interdisciplinary, you require all-in-one systems that will be helpful for all of you. Maybe just multiple use, if people are talking about the drone, other things, that is the need of the hour. Need of the hour, and that will be help for sensitizing the people also. Because when you go for like a crop, other things, you require all these things. What you require, meticulously like lectures what is given, that can be, you should meticulously see, plan, prepare a small booklet. For the KVK use for this, you can prepare a dissemination of technology, a small booklet for all this, simplified manner. Those do not. What to do, what not to do. So that will be the things for the applications of the field crop, anything cash crop, what you are working, that will be solved for there, because all Atari, most of the KVK is one drone with them, so they can read and work on that. So with this, I think anybody anything to ask? Online, anybody wanted to interact anything? Because most of the onliners are behind the screen. So many people left because
So all the participants has a email ID. I think that is very good.
Yeah.
All the material in the PDF and that manual we put and Dr. China and Dr. Ajit will put across. And also the certificate of participation, they will give you online. So
again, whole program is under an YouTube. If anybody want to share to your friends or colleagues, you can. All lectures has been posted in the, most of the lectures, I think. Last lecture also, I told everything to be posted on online. YouTube is there. The live streaming we have done for the whole program, including demonstration also. Today's program. Huh? Huh?
yeah, so we'll put on the NEPA website on the CPU website. We have also AR here. Without having drones, without going to the field, sitting here also you can learn what is this drone, what the description, sensors, and also flying. Like you, small kid, they enjoy driving the car, simulated one, simulation program we have. So that is in-house. Again, we have a couple of power sets. Goggles you can put on and fly again. This is what our experience learning center is having. So once you're ready, then you can go really, you can fly. So we are also now making drone making, how to make a drone. Virtually, all those things we are planning. My team is a bit occupied, making all those videos to push into YouTube so that we can have a large acceptability and wide for them. Okay, with this, I think on my side, and also on behalf of CP, I must thanks to each and everyone who has been here and deputed by the corresponding authority to be here and part of these active stations, both online and offline. If any query, anything, always you can connect with us. The authority with respect to fishery, fishes and aquaculture, ICAR is the concerned person for that purpose. Saman sir and China, they are working very actively and lot of aspects. As I said, first patent has come from the NEPA program from here, that's a flow-based sampling. Now cargo is going to come up very soon, the bidding is done. Sensor based again, monitoring quality, all those things we are doing. So I think CIPRI is very aggressive, very proactive, taking those technology to the precision aquaculture. Again, if you look globally also, sensors, particularly drone based, very less. And that way, I think we should be aggressive. The young researchers who are there from CIPRI or others, they should jump over, start working on this. So he has a good proposition. Since you are here, I want to again to repeat what you were asking, Dr. Sir, about the reservoir, the quality monitoring, because you have a longer depth. I said, if at all you have resources, always we can go working. We have done under ponds, very limited depth, around 4 meter, 5 meter, maximum 6 meter. But we can go for reservoir also, riverine also, provided we have those facilities. And again, I need to tell you, I had another program where we have purchased a sensor which was costing something around 2 crores, 3 crores. That is a underwater hyperspectral imaging sensor, non-imaging sensor. That is with IIT Kharagpur. They were asking me to take it. I told yes. Only it was a 2.5 hours drive. You give us the Kharagpur and we'll do those studies. And that's free of course that sensor is going to be there because I get the money for purchasing under another program, PhD program. So they are not able to handle.